What if I told you that reality is already stranger than science fiction? That your thoughts can be read, your dreams decoded, and your body rewritten like digital code? That deep in underground labs and silent rooms, lit by blinking servers, scientists have learned to move particles without touching them, stop light in its tracks, and revive organisms frozen for decades. This isn't fantasy. It's the current edge of science. In the next 4 hours, you'll enter a world where teleportation is real at the quantum level, where crystals tick through time like clocks that never wear down, and where human minds have begun to merge across electromagnetic waves. You'll witness AI predicting your illness before your body even knows it's sick. You'll see robots that teach themselves, proteins designed by artificial brains, and DNA that stores entire films. You'll confront the eerie truth that some materials can vanish under light, that quantum computers are solving problems no classical machine ever could, and that we've already captured the shadow of a black hole. This isn't a glimpse into the future, it's a quiet, current revolution happening beneath your feet. So if you're ready to question the boundaries of life, mind, and matter, if you're prepared to see the universe not as a machine, but as a neural network dreaming itself into existence, then tap like, hit subscribe, and step with me into a reality that was never supposed to feel this real. Because what you're about to learn may not just change what you know, it might change what you are. Teleportation is real, at the quantum level. Have you ever dreamed of vanishing from one place and reappearing somewhere else, as if space itself folded around your will, erasing the in-between? The thought sits at the edges of every child's imagination and lingers in the background of adult desire. The impossible made instant. A whisper of liberation from distance, delay, and the stubborn laws that bind flesh to geography. But what if I told you that this fantasy, this shimmering illusion of science fiction, has already cracked the surface of reality? Not in the future, not in interstellar laboratories, but here, now, at the heart of quantum mechanics. Beneath the structure of everything you know, your body, the air, the chair beneath you, lies a reality stranger than any fiction. A world where particles disappear from one place and reappear in another without crossing the space between. This isn't teleportation as Hollywood depicts it. No beams of light, no flickering bodies. But it's real, and it defies everything your senses trust. At the quantum level, teleportation doesn't involve motion. It involves instantaneous state transfer. Not movement, but replacement without journey. It's as if the universe deletes a particle in one place and pastes its identical twin somewhere else, not as a copy, but as continuation. And this truth is more than technical. It is unsettling, poetic, and profound because it challenges your deepest assumptions about identity, about location, about continuity. The process is called quantum teleportation, and it's not a theory. It's been demonstrated again and again in labs around the world, with photons, with electrons, even with atoms. The trick lies not in moving the thing itself, but in transferring its quantum state, the invisible essence that defines what it is, how it spins, how it exists in relation to everything else. Through a bizarre property known as entanglement, two particles, no matter how far apart, can share a single unified identity, like twins born of the same equation. When you change one, the other instantly reflects the change, not because they send messages faster than light, but because they are no longer truly separate. In this way, a quantum state, a particle's soul if you will, can be destroyed in one location and reconstituted in another with no trace of travel, no memory of in-between. The original is gone. The destination is now. And in this disappearance and reappearance lies a riddle. If the particle's state is all that defines it, and that state now lives elsewhere, is it the same particle? Is it reborn or replaced? Did it ever leave at all, or was it never fully here to begin with? This is where the boundaries between physics and philosophy begin to blur, where teleportation stops being a novelty and starts becoming an existential mirror. Because if particles, the building blocks of you, can exist in such liminality, then so can you. You are made of such particles, Your thoughts ride upon waves of quantum behavior. Your memories are entangled states in a web of neurons that never fully settle into being but shimmer between possibilities. So when we speak of teleportation, we're not speaking of just matter, but of identity. And that leads to deeper questions. Questions you can feel in your chest. What does it mean to be somewhere? To exist in a place, in a time, as yourself? If you could be teleported, fully and perfectly, would you be the same you on the other side? Or would something be lost in the handoff? Something intangible that science cannot replicate? Consciousness, soul, presence. If you vanish in one place and your state reappears elsewhere, are you transported, or is a new you created while the old one vanishes silently? Quantum physics does not answer this. It only whispers possibilities, each more haunting than the last. And yet the technology marches on. In 1997, physicists successfully teleported the state of a photon. By 2015, researchers in China and Austria were teleporting quantum information across kilometers. By 2017, Chinese scientists achieved space-based teleportation, transferring quantum states to a satellite orbiting Earth. Not someday. Already. Right now, in the sky above you, particles are vanishing and reappearing, obeying laws that once belonged only to fantasy. And while these are quantum states, not people, not objects, each step brings the line closer, blurring fiction into fact. The roadmap is uncertain, but the direction is clear. Teleportation is not only possible, it's happening, quietly, consistently, all around you. You live in a world where location is becoming optional. And yet the real power of quantum teleportation isn't in transit. It's in meaning. Because this isn't just about moving particles. It's about what movement is. It's about connection, across distance, about unity without proximity. Entanglement, teleportation's backbone, reveals a universe not of isolated points, but of relationships. Particles don't exist in isolation. They exist as echoes of each other, threads in a larger pattern. And if that's true for them, then perhaps it's true for you. Perhaps you are not an isolated self, but a distributed identity, flickering across relationships, memories, and moments. Perhaps teleportation already happens in softer ways. When someone remembers you from afar, when your presence lingers in a room long after you've left, when grief feels like the ghost of proximity. The quantum world shows that space is an illusion, and perhaps so is separation. You are entangled, not metaphorically, but physically, with every place you've been, every person you've known. The molecules in your breath once danced in the lungs of strangers. The atoms in your skin once blazed inside stars. Even without technology, you are already spread across the cosmos, woven into the fabric of everything. Teleportation just makes the invisible visible. It renders the intimate math of reality into events we can witness. And that is the strangest part. Not that teleportation is real, but that it took us so long to realize that we were never truly still to begin with. You are not static. You are not fixed. You are movement, even at rest. Every moment of your body is a swirl of disappearing and reappearing, cells dying and rebirthing, atoms exchanging, thoughts teleporting from neuron to neuron at light speed. You are a living quantum process. You are teleportation made flesh. So, where does that leave you now? Sitting wherever you are, holding a device in your hand, staring at symbols shaped into meaning. It leaves you with a choice. Not a technological one, but a philosophical one. What does it mean to be here? If teleportation is real at the quantum level, then here is negotiable. Now is layered. You is not singular, but smeared across probabilities. You are a probability field collapsing into experience. And if the universe allows particles to break the rules of space, then perhaps it's inviting you to break the rules of self. Not to destroy identity, but to expand it. To see yourself not as a point, but as a wave. Not as a place, but as a process. So the next time you close your eyes and wish to be elsewhere, know this. Part of you already is. You are entangled with every version of yourself you could become, And teleportation isn't just a scientific experiment. It's a metaphor for transformation, for reinvention, for the mysterious way that you can change entirely while still remaining you. The lab shows the principle, but life is the application. You teleport every time you let go of an old belief, every time you wake up in a new state of mind, every time you look in the mirror and see someone unfamiliar, yet true. And maybe the future isn't a place we travel to, but a version of ourselves we collapse into being. Maybe distance was always a distraction. Maybe what you call arrival is just the universe acknowledging your readiness. And so, teleportation becomes something more than quantum magic. It becomes a mirror. It asks you not just where you are, but what you are. It shows you that location is less important than relation, that continuity is less stable than you thought, and that perhaps the truest journey is the one where you disappear from who you were and reappear as someone you chose to be. You are not stuck. You are not singular. You are not static. You are the echo of possibility collapsing into now. And the question, as always, is not whether teleportation is real. It is. The question is, are you brave enough to step into the version of yourself waiting at the other end? Time crystals exist, a new state of matter that defies physics. Imagine a ticking clock that never winds down, a heartbeat that pulses without spending energy, a rhythm that doesn't fade with time but repeats eternally, like a cosmic metronome, playing a silent song in the bones of the universe. Not metaphorically, not hypothetically, but actually. Now imagine this rhythm emerging not in a far-off galaxy or some future dream of alien technology, but here, on Earth, in the cold quiet of a laboratory. Picture matter, real, physical stuff, settling into a state where time itself crystallizes, forming not in space, like snowflakes or diamonds, but in time, like frozen beats marching endlessly through the seconds. This isn't science fiction, it's science fact. A new phase of matter that physicists call time crystals. And if your instinct is to disbelieve it, good, because it breaks everything. You thought you knew. Time crystals don't just bend the rules of physics, they defy them. They refuse the slow decay we associate with motion, entropy, and life itself. They are systems in perpetual motion that do not lose energy, that repeat without exhaustion, that move without going anywhere. A contradiction not just of intuition, but of thermodynamics. And yet, they exist. In labs, in equations, in the hands of scientists who have coaxed them into being. Time crystals are real, and they're quietly rewriting the story of what matter is, what time is, and perhaps what life could be. To understand why this matters, you need to unlearn almost everything. You've been told about time. You were taught that time moves forward, like a river, like a road, like a burning fuse. That energy dissipates, that systems settle, that everything trends towards stillness. That motion consumes something. But time crystals are a kind of rebellion, a perpetual drumbeat that doesn't require fuel, that doesn't fade or flatten. They are not machines, not tricks, not violations of conservation laws. They are structures that oscillate in their lowest energy state, meaning they move even when they shouldn't. You could think of them as a kind of eternal pendulum, but one that swings not in space, but in time itself. And they don't just move forever. They only exist because they move. The motion is the structure. The beat is the object. The dance is the dancer. In traditional crystals, like salt or quartz, the repeating pattern appears in space, forming lattices of atoms locked in place. In time crystals, the repetition happens in time, creating a temporal lattice, a rhythm that cannot be changed without breaking the system. This isn't just poetic language, it's experimentally verified. Time crystals were first proposed by Nobel laureate Frank Wilczek in 2012, and after years of debate and disbelief, they were created by multiple research teams, notably using quantum systems cooled to near absolute zero, where atoms begin to reveal their most exotic behaviors. In 2021, researchers at Google using their quantum processor Sycamore, demonstrated time crystal behavior in a controlled quantum environment, a system of qubits that refused to settle, that pulsed endlessly, that remembered time not as something that passes, but as something it builds upon. And yet the deeper strangeness is not in the physics, but in the philosophy that follows. Because if time can be crystalline, repeating, structured, looped, then what is time really? You've always felt it as flow, as erosion, as change. But what if time is not a current, but a field? What if, in the right conditions, it can solidify, become modular, repeatable, like tiles in a floor or chapters in a song? That's what time crystals suggest, that the arrow of time, so sacred in thermodynamics, might have exceptions. Pockets in the universe where entropy doesn't win, where repetition doesn't require energy, where the future loops back on the present and the past whispers forward. You might ask, why doesn't this violate the laws of physics? Shouldn't something moving forever generate infinite energy? But that's the beauty. Time crystals don't do work. They don't radiate or generate power. They simply oscillate internally, like a thought circling endlessly in the mind of reality. They stay in their ground state, the lowest possible energy configuration, and yet they move. It's like finding a river that flows without a slope, or a heartbeat without a body. A closed loop of becoming. A quantum secret folded inside matter. And if that doesn't chill you with wonder, listen closer. This is not a freak exception. It's a new phase of matter. Like solids, liquids, gases, and plasma, time crystals are a whole new class, a new how of being, a different answer to the question, what can something be? Now take this further. If time can structure itself into crystals, then perhaps the flow of time we experience is not the only possibility. Maybe time is not universal, not singular, but fractured, capable of forming domains, shapes, frequencies. Maybe what we call now is just one kind of time lattice among many. And perhaps, just perhaps, your own experience of repetition, of déjà vu, of routine that feels eerily mechanical, is not just psychological patterning, but a resonance with deeper time structures, a biological echo of quantum rhythms that do not decay. Maybe what you call memory is a collapsed time crystal. Maybe the strange sense that something is happening again is not illusion, but perception of a larger repetition you cannot name. Time crystals introduce this possibility, not that time is an illusion, but that our experience of it is limited, that other kinds of temporal behavior exist, hidden in matter, waiting for the right temperature, the right isolation, the right observer, and the implications expand beyond labs. If matter can adopt this state, then future technologies could one day build systems that resist time's decay, quantum memories that don't fade, computational cycles that never require rebooting, perhaps even biological structures that bypass the traditional ticking of cells and aging. A time crystal isn't eternal life, but it is a taste of eternal rhythm, a structure that exists by repeating, that survives not by changing, but by returning. And in that rhythm lies a metaphor so human it hurts. What if survival is not linear growth, but harmonic return? What if the deepest kind of existence is not reaching forward, but echoing inward? So where does this leave you? Not in the realm of impossibility, but in a world that just became larger, more flexible, more mysterious. You've spent your life thinking time is an unstoppable force, dragging you along, demanding movement, aging, loss. But time crystals prove that within the right constraints, movement does not have to mean decay. That within isolation, patterns can survive. That perhaps what you need to remain whole is not constant progress, but consistent rhythm. We worship the idea of the new, of the next, of forward. But what if the miracle lies in stable recurrence? What if healing is not a journey, but a loop? What if meaning is found not in novelty, but in return? Time crystals ask these questions, not with voices, but with vibrations, not with arguments, but with repetition. They are the universe's way of whispering. You don't understand time yet, and maybe you never will. Maybe time is the final frontier, not of exploration, but of perception. Maybe what we call the future is just a higher harmonic of now. Maybe entropy is not the enemy but the drumbeat we haven't learned to dance to. Or maybe we were never meant to understand time fully because we are part of its music, not its audience. We are notes in the measure, not the composer. But even if you cannot grasp time, you can feel it. You can sense its weight, its flow, its pauses. And now you can also imagine it crystallized, not stopped, not frozen, but rhythmically eternal, pulsing in place. Not gone, not decaying, just repeating. A breath held between beats, a whisper caught in a loop. So the next time you feel like time is slipping away from you, remember this. Deep within the quantum world, there are places where time doesn't slip, where it doesn't fade or fall, where it holds, where it sings. The same note again and again without losing volume, without cracking. And perhaps, in those places, something is waiting. Not a machine, not a message, but a new way of being. A reminder that not all motion must end in stillness, that not all rhythms must decay, that maybe, just maybe, some parts of you, your hopes, your memories, your love, can become crystalline, repeating in someone else's mind, in some future echo of now, long after you've gone. Not because time spared you, but because time became you. Your brain can be controlled by electromagnetic signals. What if the thoughts in your head weren't entirely yours? What if the voice narrating your choices could be tuned like a radio station, gently adjusted by invisible hands? Imagine waking up one day and realizing that your decisions, what you crave, what you fear, even who you love, might not have originated in the hidden caverns of your subconscious, but were softly planted there, not through coercion, not through words, but through silent pulses of electromagnetic energy. This isn't a dystopian fantasy. It's not the premise of a sci-fi novel. It's happening, not in secret, but in open laboratories, clinics, and even approved therapies. Your brain, the seat of your memories, your desires, your identity, is not sealed shut. It's not locked behind bone and blood as you might believe. It is open, accessible. Tuning forks of electricity and magnetism can alter its rhythms, nudge its circuits, and redirect its patterns. Your thoughts are born from the orchestration of neurons firing in synchrony. And those neurons obey the laws of physics, meaning they can be reached, modulated, coerced, remotely. This is the quiet revolution of transcranial magnetic stimulation, TMS, deep brain implants, and neural interfaces, technologies that don't cut you open, but instead whisper to your mind from the outside. It is not a scream. It is not a command. It is a suggestion in the language of neurons, a persuasive hum that can shift your sense of self without you ever noticing the moment it happened. Think about how delicate your perception already is, how caffeine changes your mood, how a scent unlocks a memory, how a song can transport you back decades in seconds. Now realize that none of those triggers touch your soul. They touch your brain, and your brain tells you a story. That story is you. But what if the storyteller could be edited mid-sentence? Researchers have already used electromagnetic pulses to reduce depression, calm anxiety, restore movement to paralyzed limbs, and suppress cravings in addicts. They have altered moral judgment. They've manipulated belief. They've changed people's capacity for empathy and even religious conviction, not by argument, but by adjusting circuits. A slight pulse near the dorsolateral prefrontal cortex, and suddenly someone's willingness to forgive changes. A different signal near the motor cortex, and limbs move without the person willing them to. Not in dreams, in clinics, in peer-reviewed journals. And this raises a question that touches the very nerve of what it means to be human. If your mind can be shaped from the outside in, who are you? If a machine can influence your thoughts, where do you end and technology begin? Are you, your choices if those choices can be nudged by frequency and timing? Electromagnetic control doesn't look like mind control in movies. There are no helmets, no glowing beams. Often, it's a device the size of a paperback, pressed gently to your temple, a coil humming, a pulse delivered. And the brain, so receptive, so vulnerable in its complexity, responds. Not all at once, not dramatically, but over time, in patterns, in behavior, in belief. Imagine a future, no, imagine a present, where mental states are treated like software bugs, where sadness is debugged, where creativity is downloaded, where your sense of agency is the byproduct of bioelectric editing. This is not decades away. Neural implants, such as those developed by companies like Neuralink and Synchron, already allow paralyzed individuals to communicate by thought. Electrodes in the brain translate electrical signals into words, cursor movements, even emotions. In monkeys, they allow control of robotic arms. In humans, they promise restoration and, beyond that, enhancement. But where is the line? When does therapy become programming? When does healing become rewriting? Here's where the philosophical undertow begins to drag you deeper. If we can target the neural basis of emotion, of choice, of memory, then free will become slippery. If a magnetic pulse can change your risk tolerance, was it really you who decided to jump, to love, to forgive? And if a machine can induce those changes with no emotional context, with no understanding of your past or values, then who owns your mind? Already, we outsource our memories to devices, our photos, our reminders, our histories stored in cloud servers. Now we begin to outsource control itself. And while these tools offer miraculous healing, lifting depression that medicine could not touch, calming tremors in Parkinson's patients, restoring clarity in Alzheimer's, the same technology, in different hands, could erase memories, suppress dissent, or train minds to obey. Not through coercion, through design, through interface, through quiet reprogramming of the brain's silent codes. But perhaps the most unsettling truth is that your brain doesn't resist this. It's built to adapt. It's plastic, malleable. Every experience rewires it. Every word you hear reshapes it. And so it doesn't distinguish between a life event and a machine pulse. It rewires just the same. That's what makes this revolution invisible. Because control doesn't have to feel like control. It can feel like relief, like clarity, like you finally being yourself. But if you needed a machine to get there, who is that self really? A product of your past or of your programming? And then comes the mirror you can't look away from. If your mind is programmable, are you just a machine of flesh? A wet algorithm running on electrochemical code? And if so, can that code be hacked, hijacked, recompiled by those who understand its syntax better than you? Yet within this darkness lies a light. Because if the mind can be modified, it can also be repaired. If depression is a stuck rhythm, it can be unstuck. If trauma is a locked loop, it can be recoded. If thought itself is modular, maybe consciousness is not fragile, but resilient. A song that can be remixed without losing its soul. But resilience does not mean immunity. And this is where the urgency lies. You must ask, not just what is possible, but what is ethical? Not just what can be done, but who decides? Should governments be allowed to reduce aggression in populations? Should corporations be allowed to increase attention, motivation, compliance? Should you be allowed to enhance your focus for exams, your charm for dates, your memory for profit? Where is the line between empowerment and manipulation when the interface is your own mind? And don't assume you'll feel it when it happens. Don't assume that control arrives with chains and commands. It arrives as convenience, as therapy, as optimization. It arrives gently, like a lullaby in your nervous system, reordering without warning. And if you think you'd never consent to such interference, remember that you already do. Every time you scroll, every time a push notification shifts your focus, every time a like lights up your dopamine centers, you're being trained, rewired, gently, continuously. You are already part of the experiment. The only difference is that electromagnetic control is faster, quieter, and less visible than anything that came before. So now ask yourself, if your mind can be steered by fields and frequencies, what is sacred? What is inviolable? What part of you cannot be touched? Is there a soul beyond the circuitry, a will beyond the waves? Or are we already post-human, flesh-hosting firmware, awareness riding electric tides that can be rerouted by anyone with the right tools? Maybe the question isn't whether your brain can be controlled. It can. The real question is, who gets the remote, and what happens when they press mute? You can slow down light to a full stop in a lab. You've been taught your whole life that light is the fastest thing in the universe, untouchable, unbeatable, the ultimate pace setter of all reality, zipping through space at 299,792 kilometers per second, faster than anything you've ever known. A cosmic speed limit that even time itself seems to obey. Light is the gold standard of movement, the metric by which we measure the vastness of galaxies, the breath between seconds, the heartbeat of the cosmos. But what if I told you that in a quiet laboratory, under conditions so delicate they verge on poetic, scientists have not only slowed light down, but brought it to a full stop? Imagine that, the very symbol of speed, motion incarnate, frozen mid-flight like a hawk paused in mid-air, like a thought held in suspension, like a sentence waiting to be finished. And it wasn't science fiction, it wasn't a metaphor, it was real. It happened, right here on Earth. In controlled chambers and frigid vacuums, physicists have taken beams of light, those racing, radiant messengers of the universe, and arrested their motion completely, holding them like butterflies in stasis, their energy intact, their information preserved, their velocity zero. This is not just a scientific marvel, it is a philosophical earthquake. Because if light can stop, what else that you thought was constant, absolute, eternal, might be waiting for the right conditions to be undone? To grasp this miracle, you need to step into the strangeness of quantum optics, a field where reality bends its own spine and shows you a hidden skeleton underneath. Light, as you know, is a wave and a particle. It travels through vacuum, through air, through glass, but it behaves differently depending on what it moves through. Air slows it slightly, glass slows it more, but in a vacuum, it flies freely, its natural state, we're told. Until someone dared to ask, what if we could make a medium so strange, so precisely engineered that light wouldn't just slow, it would stop? That someone was Lena Howe and her team at Harvard in the late 1990s, using a cloud of ultra-cold atoms cooled to near absolute zero, a state of matter known as a Bose-Einstein condensate. They created a new kind of optical trap. This medium, thick not with mass but with coherence, allowed them to take a pulse of light and bring it to a full, controlled halt. No magic, no illusion, just exquisite manipulation of the fundamental forces that govern wave and field. And they didn't stop there. They stored the information the light carried, its phase, its amplitude, its identity, and later re-released it, like pressing pause on a beam of truth, and then pressing play again. Think about what that means, not just for physics, but for time, for memory, for meaning. Because light isn't just energy, it's how we see, it's how we know, it's how the universe speaks. Every photograph is frozen light. Every memory you hold of someone's face is a delayed light echo. Every star you've ever admired sent its shimmer toward you across the abyss, carried on light's back. And now we can stop that. We can pause a whisper from a star, mid-air, before it reaches your eye. We can take the very medium of vision and freeze it, like snow caught mid-fall, like thunder halted mid-rumble. And in that act, we realize something deeper. That speed is not essence. That motion is not absolute. That even the fastest thing in creation is subject to context, to medium, to conditions. And if light can stop, then perhaps change can pause. Perhaps loss can be delayed. Perhaps meaning can be preserved. In that suspended beam lies a metaphor for memory, for silence, for holding on to something that otherwise slips too fast to touch. But it goes further still. Because in slowing and stopping light, we didn't just manipulate photons, we manipulated time itself in a way. Because light is the messenger of causality. It's what connects before to after. When you delay light, You interrupt sequence, you bend chronology, you toy with the pace of experience. Light delay is time delay, and the implications ripple outward like echoes through a canyon. In the world of quantum computing, for instance, storing photons could mean holding information in perfect suspension. No heat, no degradation, no drift. In encryption, this could mean new forms of secure communication, information sent, paused mid-transmission, and resumed only when safe. In fundamental physics, it means questioning what it really means for something to move through space or to be present at all. If something can be held in stasis, yet still exist, then perhaps presence is not tied to motion. Perhaps being and becoming are separate. Perhaps you can exist without changing, wait without aging, remember without decay. And this brings us back to you, because if light can stop, what else in your life can be paused? Not in time, but in meaning. Have you ever wanted to freeze a moment, not just emotionally, but physically? To stop the warmth in someone's eyes, the stillness in a room, the whisper of an almost kiss before it vanishes into noise? You can't. Not yet. But light can. And maybe that's enough to ask the question: are we racing too fast through our own lives, assuming velocity is value, speed is success, movement is life? Light teaches us otherwise. Light, our teacher, our symbol of urgency, has shown us how to stop. Gently, purposefully, without loss, without damage. It doesn't scream when it halts. It waits. And maybe so should we. Because if the fastest thing in the universe can pause without ceasing to exist, so can you. You can sit. You can breathe. You can hold the present like a photon in a condensate, knowing that it does not vanish just because it no longer moves. You are not your momentum. You are your coherence, your clarity, your resonance, your information. And just like a beam of light held in place, you are allowed to stop, to reflect, to store, to survive unchanged for a while. The modern world tells you to keep going, to stay in motion, to chase. But the quantum world says, stillness is not absence. It is conservation. It is precision. It is preparation for the moment when movement resumes. So the next time you feel the blur of life rushing past, the blur of responsibilities and expectations and distractions, remember this: light can stop. The universe's fastest heartbeat can pause. And in that pause, there is not death. There is possibility. There is memory. There is meaning. And if that is true for photons, maybe it is also true for you. Maybe you are not meant to rush through every second. Maybe your soul, like light, was designed to pause sometimes, just long enough to preserve the shape of something sacred. Not forever, but long enough to remember, long enough to return, long enough to start again with the full power of what came before still intact, waiting patiently, silently, glowing in place. You can move things with your mind. What if the barrier between thought and action, the invisible line that divides what you imagine from what you can do, was never truly real? What if your mind wasn't a confined observer trapped inside a skull, but a force, an emitter, a transmitter, capable of stretching its will beyond the limits of your flesh? We've long believed that the body is the only interface for interacting with the world, that muscles must twitch and limbs must move if we are to shape reality. But quietly, in scattered labs and clinical trials around the world, that story is being rewritten. You, yes you, can now move objects with your mind, not in the way magicians trick audiences or comic books exaggerate, but in the very real, testable, measurable, peer-reviewed way that turns neurons into remote controllers and thoughts into commands. Through a marriage of neuroscience, engineering, and computational physics, the realm of telekinesis has crept from science fiction into scientific fact. Not as magic, but as interface. Electroencephalography, brain-computer interfaces, and neural signal decoding now allow your thoughts, those electric storms of meaning inside your cortex, to directly control robotic arms, type letters on a screen, steer drones, or manipulate virtual environments. This is not a metaphor, this is not a dream, It's happening now. The mind is beginning to reach beyond the skin. To understand this transformation, you must first understand what your mind is, not as a poetic abstraction, but as a network of electrical storms, firing with mathematical precision. Every intention you've ever had, a desire to lift your hand, speak a word, blink an eye, began as an electric whisper, a cascade of voltage in the motor cortex. These signals race down neural pathways, lighting up like cities at night, until they reach muscles and trigger movement. But what if you interrupted that journey midway? What if you captured those whispers before they reached your hands and rerouted them elsewhere, to a machine, a cursor, a prosthetic limb? This is exactly what modern brain-computer interfaces, BCIs, now do, with nothing more than an electrode, cap, or even wireless sensors placed near the scalp. Scientists can record your brain's electrical language and translate it into digital commands. You think about opening your hand, and a robotic arm obeys. You imagine moving a mouse pointer, and the cursor glides. The loop between thought and action has been closed, but with a new body, one of circuits, code, and silicon. It's not that you become a machine. It's that the machine becomes part of your body's extended self. And this isn't just a theoretical breakthrough. It's a deeply human one. For people who have lost the ability to move, BCIs offer not just function, but dignity. Quadriplegics have typed messages, played music, even flown virtual drones, all with pure thought. A man paralyzed from the neck down has fed himself with a robotic arm, moved only by imagining the action. In that moment, the impossible becomes intimate. The fantasy becomes functional. The brain, your brain, is no longer a prisoner of its casing. It speaks, it moves, it reaches, and the implications go far beyond medical recovery. Imagine gaming without controllers, workspaces where your thoughts navigate interfaces, vehicles operated by concentration, smart homes that respond to your moods, communication that bypasses language altogether. What we are witnessing is not just an upgrade in human ability, but a fundamental shift in how we define agency. When your mind can act without your body, what is the body but a vessel? And if you can move the world with your thoughts, what does that make thought? But deeper still lies a question far older than technology. What is the boundary of the self? If your thoughts can move matter, are they part of the physical world or separate from it? And if they are physical, if intentions have weight and waveform and spatial influence, then the old division between material and immaterial begins to dissolve. The soul, the mind, the self, long thought to be ghosts in the machine, start to feel like features of the machine itself. Electromagnetic in nature, chemical in execution, but no less profound. You are not merely thinking, you are transmitting. You are not confined to your body, you are casting influence. And with each advancement in neurotechnology, that influence grows. Today it's robotic arms and virtual cursors. Tomorrow it could be remote machinery, augmented limbs, synthetic sensors, perhaps even shared thoughts. As brain-to-brain interfaces begin to emerge, you are becoming a node in a network of consciousness, part biological, part artificial, all profoundly new. Yet there's something oddly ancient about it too. Mystics, yogis, monks, many have spoken of intention shaping reality, of focus bending matter. What they lacked in hardware, they made up for in belief, and now science is catching up. Not through magic, but measurement. Not through faith, but frequency. Not through prayer, but protocol. And still, the awe remains. Because when you see a person move a cursor across a screen with nothing but intention, when you watch someone pour a glass of water with a mechanical, hand directed by pure thought, you feel the walls between worlds tremble. Mind and matter are not opposites, they are partners. And we, nervous systems wrapped in biology, are learning to translate between them. The brain was always a machine, but now it is a remote. And you, listening to this, might wonder, what does this mean for me? You may not be wearing an electrode cap. You may not be hooked into a BCI. But the principle remains. Your thoughts have power. They shape your decisions. They direct your gaze. They influence those around you in ways no machine ever could. Every smile you imagine and then create, every word you think before speaking, every movement you plan in silence, these are acts of telekinesis on a subtler plane. You've always moved the world with your mind. You just didn't have wires to prove it. Now we do. Now we see. Now we understand. And so, in this strange convergence of neuroscience and science fiction, of physiology and philosophy, a new form of agency is being born, one where thought is no longer private, one where silence is no longer still, one where the boundary between idea and execution, imagination and impact is thinner than a neuron's width. The future will not be made of machines alone. It will be made of minds empowered, intentions enhanced, consciousness extended. And if that future is already unfolding, if the mind is now an instrument as real as any hand, then perhaps the greatest revolution isn't in what we build, but in what we believe about ourselves. So I ask you, if your thoughts can move matter, what else can they do? What else have they been doing, all along, without your notice? What emotions have rearranged a room? What ideas have reshaped your life? What silent, flickering impulses have moved mountains within your mind? Perhaps the next frontier isn't just brain to machine, but brain to world, brain to brain, mind to meaning. And maybe, just maybe, the universe has been waiting, not for new tools, but for you to believe that the spark in your head is not just thought, but force. We can now edit DNA with molecular scissors. Imagine if your body were a library, not metaphorically, but literally, with every cell containing volumes of ancient instructions, blueprints written in a language 4 letters long. A, T, C, and G. This language is not spoken, not heard, not even seen in any traditional sense, yet it governs your height, your heartbeat, your fears, your strengths, the curl of your hair, and the timing of your death. This script, your DNA, is older than cities, older than fire, older even than memory. It is the code that built you, line by line, cell by cell, without asking permission or offering explanation, until now. Because now, for the first time in the history of life on Earth, we can edit that code, not read it, not interpret it, not guess what it means. We can take a sentence in the blueprint of existence and slice it out with surgical precision, and in its place, we can write something new. We have discovered molecular scissors, CRISPR, that can cut the double helix of DNA as cleanly as a razor through silk. You can, right now, change the essence of what something is. Think about that. You can rewrite the recipe of a living being, and in doing so, we are no longer just products of evolution. We are becoming its authors. But to understand the weight of this moment, you must first understand the miracle of what DNA is. It is not a string. It is not a thread. It is a fractal ladder, twisted into a spiral staircase, coiled tighter than thought itself, tucked into the nucleus of each of your 30 trillion cells. If you unspooled the DNA in just one of those cells, it would stretch nearly 2 meters long. If you unspooled all the DNA in your body and laid it end to end, it would circle the sun hundreds of times, and yet all of that fits inside you, like light stored in a grain of salt. This molecule carries 3 billion base pairs, each like a letter in a cosmic poem, spelling out how your organs form, how your neurons connect, how your blood clots, how your bones grow, how your tears fall. Until recently, we could only observe this code in awe, decoding small portions, mapping genomes, comparing differences. But now we carry a pair of scissors sharper than history. We can edit genes in embryos. We can disable the instructions for disease. We can enhance crops to survive drought, engineer bacteria to clean pollution, and maybe, just maybe, design immunity to cancers that haven't even emerged yet. The scalpel of biology has become a keyboard. This power comes from CRISPR, short, for clustered regularly interspaced short palindromic repeats, a phrase that sounds like science fiction jargon but is very much real. Found naturally in bacteria as part of an ancient immune system, CRISPR allows microbes to recognize viral invaders by cutting up their DNA. Scientists realized they could harness this system, customize it, and use it like a GPS-guided scalpel to target and cut any gene in any organism. Imagine programming a drone to fly through a tangled jungle and snip one specific leaf from one specific tree. That is CRISPR. And it doesn't just cut, it guides, removes, and even replaces. With the help of enzymes like Cas9, we can open up the double helix, insert new instructions, and let the cell's natural repair mechanisms seal the wound. It's fast, it's cheap, it's precise, and it is revolutionizing not just medicine, but the very idea of what it means to be alive. And yet, you might ask, why does this matter to you? You, sitting there, listening, wondering if this is just another tool in a distant lab. But it's not, because this changes everything. Your children may one day be born immune to diseases that haunted your family for generations. Your body may be rebuilt from the inside out. Alzheimer's, sickle cell anemia, Huntington's, these may become footnotes in medical history, not life sentences. You could undergo gene therapy to repair broken instructions. Not with drugs, but with edits. It's like fixing a bug in the software of life, not treating the crash. This isn't healing, it's rewriting. But as with any power that reshapes nature, CRISPR invites questions as large as the cosmos. Should we edit embryos to eliminate deafness? Or does that silence an entire culture? Should we enhance memory, strength, height? Should we create a world where disease is optional, but inequality is biological? Will designer genetics widen the gap between rich and poor until DNA itself becomes currency? What happens when the code of life is editable like a document, but only for those who can afford the upgrade? These are no longer hypothetical debates. They are ethical earthquakes trembling beneath the surface of science. We are not just editing genes, we are editing futures. And beyond the social, there's the existential. If we can rewrite what it means to be human, what becomes of human nature? If flaws are optional, is struggle still noble? If illness is preventable, is compassion still essential? When we reach into the cell and rearrange its words, we are not just scientists, we are poets of flesh, sculptors of being. And like any artist with a chisel, we risk both creation and destruction. One wrong cut, and we may awaken dormant nightmares. One unchecked experiment, and we may alter ecosystems irreversibly. Genes are not isolated strings, they are orchestras. Change one note, and you may shift the entire symphony. And yet, the possibility remains breathtaking. What if we could give sight to the blind, not with surgery, but with genetic light switches that regrow retinal cells? What if we could end inherited blindness, deafness, muscular dystrophy, not with care, but with correction? What if your aging cells could be rewritten to behave like young ones again? CRISPR is already being used to slow aging in mice, to extend life in worms, to enhance regeneration in animals. Somewhere between the clinical trial and the whispered prayer, the idea of immortality no longer seems absurd. It feels like an engineering challenge, a biological puzzle waiting for a key. You are living in a time where life itself is no longer fixed, where destiny can be debugged, where history is no longer written in blood, but in editable code. And that should both inspire and humble you. Because for the first time, evolution is not an external force. It is a choice. One we must make carefully. One that asks not just what can we do, but what should we do? And what happens if we get it wrong? Will we regret not using this power soon enough, or using it too much, too quickly, without wisdom? And so, the question remains, if you had the scissors in your hand, would you use them? Would you slice the genes that make you who you are? Would you trim away your fears, your faults, your fate? Or would you leave the code untouched, scars and all, to remain something evolved, not engineered? Perhaps the greatest editing tool isn't CRISPR, but conscience. And maybe the code that truly defines us isn't ATCG, but the choices we make when holding the power to rewrite. AI can predict diseases years before symptoms appear. Imagine if your reflection in the mirror knew something you didn't, something about your future, your fate, your unraveling. Not just how you look now, but how you will look when your hands tremble uncontrollably, when your memory evaporates like breath on glass, when your cells rebel against your body in silence before a single symptom dares to show. Now imagine if, instead of a mirror, it was a machine, silent, tireless, unblinking, watching your data trail like a shadow that follows you through time, piecing together not who you are, but who you are becoming. This is no longer science, fiction. This is the quiet revolution unfolding beneath your fingertips, beneath your skin, beneath your decisions. Artificial intelligence can now predict diseases before they appear, sometimes years, even decades, before you ever feel the first crack in your health. And what it sees is not just numbers. It sees patterns in your heartbeats, tremors in your voice, subtleties in your typing rhythm, micro-expressions on your face, and electrical murmurs in your brainwaves that whisper of futures you haven't lived yet. You don't notice these signs, but it does. And in this new frontier, your future is not something you wait for. It's something you calculate. Let that sink in. Your body is constantly leaking secrets. Your walk, your sleep, your size, your blood chemistry, your eye movements. Every one of these is a data point, a breadcrumb along the winding path of your biology. AI systems, fed on millions of such fragments from millions of people, learn to recognize the slow, hidden changes that precede disease, the slight irregularity in a heartbeat that whispers of future arrhythmias, the tremble in a finger that murmurs Parkinson's years before it shouts, the glitch in your speech that softly foreshadows dementia. This is not diagnosis. This is divination by computation. It's not telling you what is, it's telling you what will be. And suddenly, the idea of destiny becomes something editable, debuggable, interruptible. The great silent invaders of the body, cancer, Alzheimer's, diabetes, ALS, have always worked in the shadows, striking only when you're already weakened. But AI doesn't wait for war to break out. It listens at the borders. And when it speaks, it says, "You are not sick yet, but you're walking toward it." But how does it do this? How can a machine, which feels nothing, predict what a human will suffer? The answer is as eerie as it is elegant. Pattern recognition at scales your brain could never handle. Your doctor may see a patient. AI sees a cloud of variables evolving in real time. Your genome, your proteome, your microbiome, your lifestyle, your digital exhaust, each feeding into neural networks that process, compare, and simulate millions of possible timelines. These systems don't understand disease the way humans do. They map it probabilistically, learning from datasets of terrifying size and complexity. They don't need to be conscious to be prophetic. They just need to be accurate. Some models can now detect breast cancer in mammograms years before a radiologist can. Others predict diabetic retinopathy, heart attacks, strokes, even suicidal tendencies, all from patterns humans can't consciously perceive. In this world, intuition is replaced with inference. Instinct bows to iteration. Medicine becomes mathematics. And you become a probability distribution waiting to be collapsed. But here's the unsettling part. You don't even need to tell it anything. Your wearable device already does. Your smartwatch, your smartphone, your fitness tracker, they are extensions of your nervous system now. Every step you take, every pause in your breathing during sleep, every change in your heart rate variability is silently recorded, tagged, analyzed. You don't know how sick you are, but your device might. And when all these signals are fed into machine learning models trained on vast health databases, the result is a mirror that sees deeper than skin. You might feel fine today, but the data says otherwise. The AI says, you're 5 years from cognitive decline. Or, your pancreas is beginning to betray you. Or, the rhythm of your life carries the beat of an approaching collapse. It's like standing in front of a time traveler who won't tell you your whole future, just enough to warn you before you fall. And so we arrive at a new kind of existential dilemma. Not, what disease do I have, but, do I want to know the disease I don't have yet? Because foreknowledge is power, yes, but also a burden. Imagine knowing, at 30, that AI predicts you'll develop ALS at 48. What do you do with that knowledge? Spend 18 years fighting it, or fearing it? Do you live more fully or more fearfully? Do you become more alive or more paralyzed by anticipation? AI gives you answers, but not always peace. It predicts, but doesn't always prevent. You might know your future, but you might not be able to change it. This is where science collides with philosophy, where medicine becomes prophecy and healing becomes a psychological puzzle. You are no longer just a patient, you are a forecast. Yet there is light in this uneasy horizon. Because with enough data, AI doesn't just predict, it intervenes. It can recommend lifestyle changes that lower risk trajectories. It can tailor treatments years before symptoms appear. It can work alongside doctors to create custom prevention plans, nutritional, pharmaceutical, behavioral, that turn probability into possibility. And when paired with genomics, AI becomes even more powerful, understanding how your unique genetic makeup influences disease risk, drug response, and environmental sensitivity. This is personalized medicine, not as a slogan, but as a system. Imagine your phone alerting you, not to check your messages, but to check your liver enzymes. Or your watch vibrating, not to tell time, but to tell you it's time to change course before the storm hits. This is not the future. This is happening now. Hospitals are already implementing AI systems that predict patient deterioration hours before nurses would notice. Google's DeepMind has built models that outperform humans in diagnosing over 50 eye diseases. Bioinformatics firms can forecast cancer recurrence from a single drop of blood. Even mental health is being mapped, with algorithms analyzing speech, posture, and online behavior to detect depressive episodes days before they surface. In one study, AI predicted suicidal ideation with 92% accuracy based on social media posts. It's not just about what's happening in your body. It's about the silent patterns of your life. Your future has never been more visible or more vulnerable. And yet, even with all this power, the question remains, should we know everything about our future health? What happens when we find out things we were never meant to know? Is every warning a gift or a curse? Will insurance companies use these predictions to discriminate? Will employers demand genetic risk reports? Will the anxious become more anxious and the healthy become hypochondriacs? The line between helpful and harmful may be as thin as a synapse. Prediction without compassion becomes surveillance. Insight without support becomes burden. Technology without ethics becomes tyranny. The machine sees, but does it care? And so, the burden falls back on you. Would you want to know the disease growing in the distance of your own timeline? Would you dare to look if the mirror showed your decline long before it began? Would you trust the machine that never sleeps, that never lies, that never forgets, but also never feels? Maybe the deeper question isn't whether AI can predict disease, but whether humans can carry the truth of that prediction without being broken by it. Maybe some futures are best left uncertain. Or maybe, just maybe, knowing is the first step in rewriting destiny. Not with fear, but with foresight. Because in the end, the most advanced algorithm can only tell you where the path seems to go. But you decide whether to follow it, to change it, or to build an entirely new one. And perhaps, in a world where machines see everything coming, your greatest act of defiance is to live, not by prediction, but by presence. Brain-to-brain communication has been achieved between humans. There was a time when silence was impenetrable, a boundary between minds, a sacred distance where thoughts curled quietly within the cage of your skull, safe, unseen, and ultimately unknowable. But what if I told you that boundary is dissolving? That somewhere in a lab, Not a metaphor, but a literal place of wires and white coats. One person thinks, and another responds. No words spoken, no gestures made. Just brain to brain, idea to idea, signal to signal. Not imagination, not magic, but electrical pulses guided by science. Brain-to-brain communication has been achieved between humans. You live in an era where thought can leap the airless void between skulls like lightning bridging storm clouds. And that changes everything. Not just about how you speak, but about what it even means to be you. If someone else can access your intentions before you act, your perceptions before you name them, your images before you describe them, then where do you end and they begin? We once believed the mind was locked inside its biological fortress, a singular private domain fenced in by flesh and bone. But now, neuroscience is chiseling away at the walls. Electrodes, EEGs, transcranial magnetic stimulation, optogenetics. These are the new languages of telepathy. In one experiment, a subject in India imagined moving their hand, and a subject in France received the signal, their hand twitching in response, not from suggestion, but from direct neural stimulation. In another study, one rat navigated a maze, while another, blind to the layout, completed the same route through brain-to-brain transmission alone. And then came the human trials, pairing gamers, pilots, and problem solvers. One person thinks of a binary yes-no answer, and the other, across a network, receives a flash of light in their brain, recognizing it as meaning. Bit by bit, thought by thought, we are building the scaffolding for something once reserved for science fiction, a shared mind space. But this isn't reading minds in the psychic sense. It's more intimate, more technical, more disturbing. What's being shared isn't polished language or reasoned thought. It's raw neural intent. It's not, I want to raise my hand. It's the spike of electrical activity in your motor cortex milliseconds before you even realize you're moving. It's not, I saw a cat. It's the retina to occipital lobe signal pulsing with feline pattern recognition. These brain-computer interfaces, BCIs, bypass speech, culture, and even consciousness. You don't express a thought, you transmit its electrical signature. This is not telepathy of the soul, it is telegraphy of the cortex. You are not conversing, you are syncing, and it all starts with decoding. Neuroscientists have learned to map brainwave patterns to specific thoughts, emotions, or intentions. You think of moving left, and a distinct electrical pattern appears. You recall a face, and a different pattern lights up. Using machine learning, we can now train algorithms to recognize these signals and associate them with actions. The reverse is also true. Signals can be sent into the brain, stimulating neurons to cause the experience of movement, vision, even memory. Combine these two processes, reading and writing, and suddenly the nervous system becomes a two-way radio, a sender and a receiver. And between them, no words, just pulses, just light, just thought. The implications are staggering. Imagine coordinating a rescue operation where responders think instructions into each other's minds. Imagine astronauts on Mars solving emergencies without speaking. Imagine a parent sensing a child's fear, not through expression, but through direct neural transmission. Now imagine a world where soldiers are networked like drones, where interrogations bypass lies and dig straight into memory, where governments can extract, not ask, what you know. The same technology that enables intimacy can enable invasion, because the mind, once readable, is no longer sovereign. And here you are, sitting in front of this truth, perhaps still believing your thoughts are yours alone. But already, wearable EEG headsets exist that detect concentration, relaxation, frustration. Gamers use them to control avatars. Students use them to train attention. Artists use them to make music by thinking. These are primitive forms, yes, but so were dial-up modems before the internet swallowed the world. The future is a brain net, where minds connect like servers, syncing real time, pooling cognition like cloud computing pools memory. In that future, privacy becomes mythology, individuality becomes questionable, and identity becomes porous. Ask yourself, if someone else can experience your thoughts as their own, Are you still you? If your mind becomes a signal among others, where does selfhood live? We built language to bridge isolation, but brain-to-brain tech removes isolation itself. It doesn't need symbols. It doesn't need translation. You don't describe what you feel. You transmit the feeling itself. It's empathy with no ambiguity, understanding with no misinterpretation, but also vulnerability with no shelter. In such a world, deception dies, but so might freedom. And yet, there is beauty here too, a potential for unity that words never achieved. Imagine lovers sharing dreams in their rawest form. Imagine therapists feeling what patients cannot say. Imagine teachers uploading understanding directly into curious minds. Imagine consciousness, not as a singular flame, but as a constellation, each brain a node, lighting up in synchrony. In this future, connection is no longer poetic, it's literal. Loneliness becomes a technical failure, not a human condition. We evolve not through genes, but through neural collaboration. But at what cost? You are not just your thoughts. You are the silence between them. You are the hesitation, the internal conflict, the unspoken. If every flicker of intent is exposed, if every raw impulse is shared, do we lose the dignity of privacy? The mystery of the self? Will people curate their inner lives as they do their social media profiles? Cleaned, filtered, performative. Will your thoughts be yours, or will they be optimized for transmission? When your brain is always plugged in, do you ever truly rest? This is the threshold you now face, not in theory, in prototype, in research papers and corporate labs, in startup pitches and DARPA grants. Brain-to-brain communication isn't waiting for permission. It is being built. And as with all great technologies, it is neutral until it meets human hands, or in this case, human minds. And minds, as history has shown, are both miraculous and monstrous. So, where does that leave you? With a question, perhaps. If a stranger could see your dreams before you do, feel your fear before you flinch, answer your question before you ask, would you feel more understood? Or would you feel more exposed? Because in this emerging reality, connection is no longer optional. It's incoming. We've created synthetic life from scratch. Imagine waking up in a universe that didn't know what life was. No cells, no breath, no birth, no death. Just sterile elements drifting in infinite silence, waiting for accident or divinity. Then imagine, in a gloved hand under fluorescent lights, that silence is broken, not by evolution or fate, but by you. You, standing above a petri dish like a god in a lab coat, assembling molecules not to understand life, but to create it. Not to copy it, not to clone it, but to make something truly new, alive, and yet never born. That is no longer fiction. We have created synthetic life from scratch, and if you think this is merely science advancing, you are missing the tremble beneath the achievement, the shift in the very definition of life, the moment we stepped from decoding biology to designing it, the instant we stopped studying nature and started replacing it. This isn't about controlling bacteria or splicing genes. This is about manufacturing life from non-life, about becoming the author of biology, not its reader. For centuries, we assumed life had to come from life, a sacred continuity stretching from cell to cell back to some ancient primordial soup. Even the boldest biologists saw themselves as editors, never creators. But in 2010, the team at the J. Craig Venter Institute shattered that notion. They didn't just modify an organism, they built one. They synthesized a genome from raw chemicals, coded it with carefully selected genes, and inserted it into a hollowed-out bacterial shell. And then, it booted up. It lived. It replicated. It consumed, divided, and evolved. For the first time in Earth's history, a creature existed that had no evolutionary ancestor. Its mother was silicon, its father was code, and its soul, if it had one, was typed into being. It was the first organism with a synthetic genome, an artificial software running on a biological machine. And in that moment, the question changed from, can we create life? 2. What kind of life will we choose to create? You may be tempted to shrug this off as bacterial tinkering, harmless in its smallness, but you would be wrong, because life doesn't care about scale. It only cares about function, and these synthetic cells function. In fact, they function better. Biologists can now design organisms with built-in kill switches, metabolic enhancements, or chemical production capabilities that no natural cell could evolve. Need a microbe to clean up an oil spill? Design one. Want bacteria that photosynthesize in the dark? Engineer it. Dream of cells that detect disease, deliver drugs, or produce food out of air? Write the code and press print. The cell becomes a chassis, a blank canvas, a programmable vessel. DNA becomes software. Life becomes technology. And when life becomes technology, everything changes, not just in medicine or industry, but in philosophy, in ethics, in identity. Because now, when you look at a flower or a fish or a child, you no longer know for sure if it came from nature or design. The line between living and built begins to blur. If a synthetic organism reproduces, mutates, and evolves, is it not alive? If it dies, is that not death? And if it thinks, if it ever thinks, would that not be a soul? We are not just making tools, we are making selves. And selves, once made, do not stay obedient. But let's step back. What does it mean to create life from scratch? It means we no longer rely on existing organisms to birth new ones. It means we can build genomes base by base, encoding whatever functions we desire, then insert them into an empty cellular shell and let the system run. It means life is no longer an emergent mystery, it is a manufactured process. Already, companies are producing synthetic yeasts to brew medicines, biofuels, and rare enzymes. Labs are exploring synthetic algae that can terraform environments. And CRISPR, once just a gene editing tool, is now being combined with synthetic biology to create organisms that can reprogram their own genomes dynamically. You might be wondering, where does this end? Could we one day create a human from scratch? Not clone, not genetically modify, but build, atom by atom, chromosome by chromosome, a person who never had parents, never had a womb, never had a childhood, but opens their eyes nonetheless. Science is not there yet, but the logic is unfolding. Already, we can synthesize every gene in the human genome. We can build functional synthetic embryos that mimic early development. Artificial wombs are being tested. AI-designed proteins fold better than anything evolution produced. Put these threads together, and you see the tapestry forming. Not tomorrow, not next year, but not science fiction either. And here's where you come in. Because this isn't just a story about scientists and silicon. It's about what kind of life you believe deserves to exist. If we can create life with no ancestry, does it have rights? If we delete suffering genes from embryos, are we saving them or robbing them of something essential? If we program love, fear, or memory into synthetic brains, are they feeling or simulating? And if we one day meet a life form entirely synthetic, but indistinguishable from ourselves in mind and manner, do we greet it as kin or reject it as counterfeit? Because somewhere deep in your psyche, you probably still believe life is sacred, because it is natural, because it came from struggle, chance, and billions of years of blind evolution. But now, life can come from design, from intention, from lab notebooks and DNA printers. Does that make it less sacred? Or more? What is more divine? The universe stumbling into complexity, or you deliberately shaping it? Is humanity desecrating life by building it or fulfilling its ultimate purpose? And if you could hold in your hand a vial of liquid containing a creature never before imagined, never born but breathing, never evolved but evolving, what would you see? A miracle, a monster, a mirror. This is no longer theoretical. We are creating organisms from scratch, and each step forward removes another barrier between life and machine, between evolution and engineering. And like all revolutions, this one moves faster than your mind can adjust. What you consider today as strange, tomorrow will be standard. the impossible becomes normal, and the normal becomes forgettable. But let us not forget. Let us look, without blinking, at what we are doing, not imitating life, but initiating it. Not exploring creation, but becoming creators. And with that comes a responsibility beyond any science, any law, any precedent. Because when you build something that can build itself, when your creation becomes a creator, you are no longer in control. You are in dialogue with something new, something alive, something that carries your intention like a seed and plants it in the soil of the unknown. So I ask you, if life can now begin wherever we choose to spark it, then what does it mean to be born? And more hauntingly, who decides what deserves to live? Scientists are building living machines from frog cells. Imagine if life was no longer a gift given by nature, but a toolkit you could assemble, one cell at a time, until motion, memory, and purpose emerge not from instinct, but from design. Picture a creature that isn't born but compiled, not evolved but constructed, not with wires and metal but with muscle and skin, pulsing with the quiet rhythm of life, yet answering to no evolutionary tree, no genetic ancestry, no ecosystems. Logic. Now imagine this creature, no larger than a grain of salt, swimming through fluid, not by reflex, but by programmable intention. This is not science fiction. This is real. You are living in a time where scientists are building living machines from frog cells, where biology and robotics are no longer separate realms, but overlapping brushstrokes on the same canvas, painting futures that no ancient life form could have imagined. These aren't robots, and they aren't animals. They are xenobots, living, programmable organisms assembled from skin and heart cells harvested from frog embryos, reconfigured into forms nature never invented, and trained to complete tasks like moving toward a target, carrying objects, or even repairing themselves. And suddenly, the definition of life, of organism, of purpose, of will, begins to shiver and melt like warm wax beneath a microscope's gaze. They began as an experiment in morphological freedom, a test of what could happen when you stop asking what life is supposed to be and start asking what it could be. At Tufts University and the University of Vermont, researchers used a supercomputer to simulate thousands of cellular configurations, optimizing shapes and movements, not for survival in the wild, but for functionality in digital space. Once they had a design that moved purposefully, they went to the lab. They took skin cells, which would normally become part of a tadpole's body, and heart cells, which rhythmically contract. These were not genetically modified, not programmed with external code, just arranged precisely into a shape dictated by algorithm. Then they placed these cells in a petri dish, and they moved, they walked, they swam. Not because of instincts or neural commands, but because the configuration of their cells made it possible. Form created function. Structure created behavior. The body became the brain. You might want to call them robots, but they are not. Robots, traditionally, are constructed from metal, circuits, silicon, and code. These are constructed from life itself. There are no wires, no processors, no electricity, only living cells arranged in novel architectures, and yet they perform programmed behaviors. They can self-organize, they can repair minor damage, some can even reproduce by collecting loose cells and assembling them into new versions of themselves, a biological recursion that nature didn't invent, but humans did. These xenobots are simultaneously alive and artificial. They are biological, machines, self-powered and biodegradable. And unlike traditional robots, they leave no electronic waste, no battery acid, no toxic residue, only carbon and memory dissolved in water. But here's where it gets strange. Philosophically, not just biologically. Because when you create a living system that doesn't fit into existing categories, you begin to question the categories themselves. Are these organisms? They have no nervous system. They do not eat. They do not sense the world in the way we define perception. But they move. They adapt. They function. Are they machines? They are not assembled from parts but grown from cells. They are soft, autonomous, and healing. Are they alive? They are not born. They do not reproduce naturally. They do not evolve. And yet they live. So what is life? Is it origin, behavior, DNA, consciousness, or is life whatever reacts, adapts, and endures? You might think this is a niche experiment with no real-world consequence, but you would be wrong. The potential applications are staggering. Imagine deploying Xenobots into your bloodstream to deliver medicine precisely where it's needed. No pills, no injections, just living couriers. Imagine microscopic cleaners that can remove plaque from arteries or toxins from groundwater. Imagine programmable life forms that dissolve after completing their task, leaving no trace but healed tissue or purified water. This isn't science fiction. These are real, viable avenues being tested now. And as AI becomes more sophisticated and biological engineering becomes more precise, the Xenobots of tomorrow could be far more complex, capable of learning, adapting, maybe even coordinating like microbial colonies or insect swarms. But with power comes risk. If we can build life, we can weaponize it. If we can create cells with purpose, we can create cells with agendas. The same technology that lets us build biodegradable helpers could let someone build targeted pathogens, biological trackers, or organisms that replicate beyond control. There are no hard limits here, only ethical ones. And ethics, as you know, often lag behind invention. Are we building tools or species, helpers or hybrids? When a Xenobot replicates itself, is it merely following instructions, or has it crossed into the realm of agency? Who is responsible if something goes wrong? Not the cells, but their creators. And if you created a Xenobot with neural tissue, if it one day felt pain or preference or purpose, would it deserve rights? Could we enslave it, discard it? Or would we owe it the same respect we give to animals, or even to each other? The line is blurring. Synthetic biology is not just giving us new tools, it is forcing us to redefine moral boundaries. A machine that is alive is one problem, but a life form that can be programmed like a machine, that's a paradox we are just beginning to face. You live in a world where the raw materials of life are no longer sacred. They are plastic. You can shape them, instruct them, remix them. Life has become an interface. Nature is editable. Biology is programmable. And intelligence, once confined to brains and instincts, is now a matter of arrangement. A few heart cells pulsing in a new geometry, executing motion without a mind. The first step has been taken. The leap has begun. The question now is not whether we can build life, but why we build it, and for what. And so I ask you, if you stood over a dish, watching cells you assembled take their first synthetic swim, what would you feel? Awe? Ownership? Responsibility? If we can create living things with no lineage, no evolution, and no past, what does that make us? Designers? Parents? Gods? Or just another species, too curious to leave the universe alone? Quantum computers can solve problems. Classical ones never will. What if the way you've always understood thinking, sequential, deliberate, step by logical step, was only a dim shadow of what thought could be? What if your mind, as intricate as it feels, is still walking barefoot on the surface of reality, while just beneath it lies a swirling ocean of infinite possibility, where every decision, every outcome, every version of every problem branches off into shimmering echoes. And there exists a kind of machine that doesn't choose a single path, but walks them all at once. Imagine solving a maze not by running through it, but by becoming the entire maze, feeling every wall, every corner, every route simultaneously until the solution reveals itself, not as an answer, but as a collapse of potential into certainty. That's what quantum computers are beginning to do. Not faster guesses, not better code, a different kind of logic altogether. While classical computers think in ones and zeros, black and white, doors open or closed, quantum computers think in possibilities, in shadows, in blurred realities that only become fixed when observed. They are not just faster machines, they are machines that think in parallel worlds. You live in a world where such devices already exist, humming in supercooled chambers, computing not with bits, but with qubits, quantum bits that hold multitudes, that can be both 1 and 0 until forced to choose. And they're beginning to solve problems classical computers will never even begin to approach. Not because they're better, but because they're different in ways our minds can barely comprehend. You've likely heard the comparisons. Classical computers are like light switches, on or off, while quantum computers are like dimmer dials rotating in 360 degrees, spinning in a dance of probabilities. But even that metaphor is too tame. Qubits are not just about probability. They exist in superposition, meaning they can be in multiple states at once. A classical computer exploring a problem searches one possible solution at a time, like a flashlight scanning a dark room. A quantum computer becomes the room. It explores all possibilities simultaneously. The result? Certain problems that would take a classical computer longer than the age of the universe to solve could, in theory, be cracked by a quantum machine in minutes. Not just a speed boost, a dimensional leap. These machines don't process. They resonate. They don't calculate. They collapse possibility into resolution. But how does this work? To understand that, you need to abandon the safety of classical logic. In a quantum system, entanglement allows qubits to be linked such that the state of one instantly affects the other, no matter how far apart they are. This isn't a metaphor. It's a verified phenomenon Einstein once called spooky action at a distance. Imagine having a key in New York and its matching lock in Tokyo, and the moment you turn the key, the lock opens. No signal, no delay. This allows quantum computers to hold vast amounts of information in fewer qubits than classical systems could ever dream of. But it comes at a cost: decoherence. The fragile nature of quantum states means any disturbance, heat, light, noise, can cause the whole system to collapse into a classical state, losing its quantum magic. That's why these computers operate in extreme cold, often near absolute zero, inside chambers more isolated than deep space. And yet, even in their infancy, these machines are already showing promise. Quantum computers have factored large numbers, an impossible task for classical systems at scale, threatening to crack the cryptographic codes that protect your bank accounts, your secrets, your entire digital world. They've simulated molecular interactions so complex that classical computers stall at the starting line, opening pathways to design new medicines, materials, and catalysts. They've begun optimizing solutions to logistics problems with more variables than atoms in the universe. These are not theoretical ideas. Companies like IBM, Google, and D-Wave have built functioning quantum devices. Governments are investing billions. Algorithms like Shor's and Grover's have shown mathematically that quantum advantage is not just hype, it's a new epoch in computation. But here's the deeper, more unsettling truth. Quantum computers are not just machines. They are mirrors, reflecting a different way of knowing, a way of thinking that defies your intuitions. They don't try paths. They exist in all paths. They don't compute answers. They collapse the wave of the universe to produce a result. And if such a machine can outperform our most advanced supercomputers by doing something we cannot replicate with silicon, what does that say about our minds, our limitations, our logic? Is reality itself more quantum than classical? And are we only just now building machines that think the way nature has always processed information? And then there's the philosophical tension, because if a quantum computer can explore all realities simultaneously, what happens to choice, to consequence? If we can model molecules, simulate evolution, or forecast pandemics with eerie precision, are we rewriting prediction itself? Are we about to build a machine that not only answers our questions, but asks better ones than we can even imagine? And if quantum computers surpass human cognition in certain domains, not in brute force but in paradoxical elegance, what will our role become? Will we be the programmers, the supervisors, or simply the biological stepping stones in a quantum evolutionary leap? The more you understand these machines, the more they resemble dreams. Not because they're vague, but because they're real in a way your everyday logic resists. A dream doesn't follow cause and effect. It leaps. It links ideas through feeling, association, resonance. A quantum computer links probabilities through interference, coherence, and entanglement. Your mind wakes in one timeline. A quantum processor wakes in all of them. And that shift, from deterministic to probabilistic, from binary to blurred, is not just technological. It's philosophical. We are beginning to think differently, to build tools that no longer extend the hand, but extend the imagination itself. So now the question is not what problems quantum computers will solve. It's what questions they will force us to ask. Will they teach us new physics? Will they reveal patterns in biology, in markets, in the brain that we couldn't see because our logic was too narrow, our math too shallow? Will they design new life, crack consciousness, simulate entire worlds for us to explore or even live in? The frontier isn't just technological, it's existential. These aren't just faster tools, they are the beginning of machines that can dream with precision, fantasize with equations. They don't only predict weather, they may predict us. And in the end, as you stare into the cold chamber of a quantum processor, watching the flicker of superconducting loops or trapped ions dancing at near zero temperatures, what are you really looking at? A machine? A mirror? A mind? Or the first whisper of a future where reality itself becomes programmable, and where your understanding of possible will need to be rewritten? Because quantum computers won't just solve problems. Classical ones never will. They'll reshape the very idea of what a problem is. We can read your dreams using brain scans. What if I told you that even the most private sanctuary you've ever known, the inner theater of your dreams, that strange cinema of impossible places and forgotten faces, was no longer locked away behind your skull? What if science, with quiet determination and cold precision, had begun to slip into that theater while you slept, sitting beside you in the velvet dark of your unconscious mind, recording the phantoms on the screen? You may think of dreams as yours, untranslatable, untouchable, made of vapor and metaphor, beyond the reach of instruments and algorithms. But right now, in a laboratory lit by humming screens and the soft breath of machines, your dreams are being watched, not metaphorically, literally. With functional MRI scanners, deep learning algorithms, and years of neurological mapping, scientists have begun to peer into the brain not just to measure activity, but to reconstruct imagery. They're not just recording the fireworks of neurons, they are decoding them, turning pulses of blood flow into approximations of pictures. Reading the language of dreams not with poetry but with math, and in doing so, they are dismantling one of the last sanctuaries of solitude humanity has ever known. You've always believed your dreams are a place the world can't follow, a place where laws of logic bend, where gravity gives way to meaning, where time can loop, stretch, or freeze altogether, a place beyond language. And yet, in 2013, researchers from Kyoto began translating brain activity during REM sleep into rudimentary images using fMRI scans. Participants would dream, wake, and describe what they saw. Then algorithms were trained to correlate those verbal accounts with the neural signatures recorded while they slept. Over time, the machines got better. Not perfect, but shockingly close. When someone dreamed of a man, or a house, or a dog, the system began to reconstruct ghostly approximations of those shapes, fuzzy silhouettes of thought itself. The boundaries between imagination and perception began to blur, between biology and cinema, between you and the observer. And it didn't stop there. Other experiments began decoding not just visuals, but semantic content. Dreams of movement, fear, intimacy. Soon machines weren't just seeing your dreams, they were understanding them. Consider what that means. If machines can map your mental imagery, then your inner world, your memories, your fantasies, your fears, may one day be screened like a movie. Think of the implications in courtrooms, in therapy, in relationships. Think of dream diaries not written in ink, but in neural code. Imagine lying still, dreaming of flying over cities made of sound and waking to find that vision rendered in pixels before you. Will it be beautiful or invasive? Will it feel like magic or violation? You might say, but dreams are random, chaotic, nonsense. And yet they follow deep symbolic currents, patterns as old as myth, shaped by memory, fear, longing. If machines can map these symbols to neurons, then meaning itself becomes a signal, decodable. And where does that leave privacy? If the mind is no longer a locked box, but a broadcast station emitting electromagnetic whispers, then what is left of you that is only yours? Already, brain-computer interfaces like Elon Musk's Neuralink promise real-time readings of intention, thought, even imagined speech. Already, AI is being trained to translate those impulses into action. You imagine a movement, and a robotic arm performs it. You picture a sentence, and the text appears on screen. How far is the leap from intention to imagery? From thought to dream? From dream to shared virtual space? You're standing at the edge of a new era, where inner life becomes outer technology, where consciousness is externalized. But here's the paradox. In making dreams visible, are we reducing them? What happens to mystery when it is rendered? What happens to meaning when it becomes data? If a dream of your childhood home can be visualized, will it still feel the same? Will it lose its emotional power, its vagueness, its ability to heal, terrify, or inspire? Or will we enter a renaissance of internal cinema, a new art form born from the fusion of neuroscience and imagination? Perhaps you will one day compose dreams like a director, feed your mind a neural storyboard, and dive into custom-made subconscious journeys. Perhaps therapy will be guided by dream playback, or love explored through shared unconscious experiences. Maybe, just maybe, we're on the brink of emotional telepathy. And yet, something in you resists. Because dreams are not just stories, they are reflections. The moonlight on the lake of your mind, they are truth told sideways. They speak in riddles for a reason. Would knowing too much dissolve their wisdom? If a machine tells you what your dream means, will that feel like revelation or robbery? You see, dreams are where your soul rehearses being human, where it puzzles through grief, rehearses joy, processes trauma. If we mechanize that, do we risk flattening the self, reducing spirit to signal? But maybe not. Maybe, just maybe, this is evolution. Maybe humanity is building the tools not to invade dreams but to honor them, to listen to them with more than interpretation, with technology, like listening to whales by translating their clicks, like deciphering ancient languages, not with guesses, but with quantum computation. What if decoding dreams is not the end of magic, but its continuation in a new dialect, a deeper empathy, a new mirror for the soul? So now, as you close your eyes tonight and drift into that soft abyss where gravity turns to metaphor and identity loosens its grip, remember this: somewhere, someone is building a machine that might be watching, not your body, not your breath, but your dreams. Not to steal them, to understand them, to replay them, to show you what you already knew but couldn't yet see. The question is, when they play it back, will it still feel like you? Or will it feel like something else has dreamed? Robots can now learn without being programmed. Imagine teaching a newborn not through speech or demonstration, but by letting it wander blind through the world, touching walls, bumping into furniture, feeling heat and cold, falling and rising again. And through those collisions alone, it begins to understand. Now imagine that child is made of metal and code, that it has no nervous system, no hunger, no instincts, and yet somehow, through a series of mechanical stumbles, it starts to learn not because you programmed what it should do, but because you gave it the capacity to learn for itself. This isn't science fiction, it's happening now. Robots can now teach themselves tasks you never explicitly showed them, by trial, by error, by adaptation. We have created machines that no longer follow static instructions, but write their own rules based on feedback. Reinforcement learning, in neural networks, and self-supervised algorithms have birthed a new kind of intelligence. One that learns not by being told, but by experiencing. And with each experiment, each simulation, each real-world tumble, they grow smarter. Not with our knowledge, but with something that looks startlingly like their own. You were raised to think of computers as obedient, precise, literal. A computer was a servant, doing only what you asked and nothing more. But machine learning flipped that script. First came supervised learning. You gave the machine labeled examples, and it memorized patterns. Then, unsupervised learning. You gave it data without labels, and it discovered structures on its own. But now comes something deeper. Reinforcement learning. You give it a goal, a reward. It doesn't know how to achieve it. It stumbles, it guesses, it fails. And then miraculously, it succeeds. And when it does, it remembers. It builds internal maps. It forms strategies. And all without being taught in any conventional sense. We don't code its answers. We build a system that codes itself. One algorithm playing millions of games of Go against itself until it becomes unbeatable. One robot hand juggling a cube, failing 1,000 times until it learns just how to twist it. And perhaps even more eerily, it learns things we ourselves don't understand. When AlphaZero mastered chess, it didn't just mimic grandmasters, it discovered new strategies no human had thought of. The student has become the explorer. And now, this intelligence is stepping out of the digital and into the physical world. Robots with camera eyes and jointed limbs are now being trained through reinforcement, not rules. They learn to walk by falling, learn to grip by failing. They receive no instructions, only a reward signal when they succeed. This is the strange, new code of learning without programming. And the more complex the task, the more creative the failures. One robot learns to run, not by mimicking animals, but by creating its own awkward, chaotic gait and then refining it. Another learns to sort objects it's never seen before. Another plays hide and seek and invents deception, without ever being told what deception is. These are not coincidences. They are the emergence of behavior. Patterns born not from logic, but from dynamics. We don't tell the robot how to win. We just reward winning, and it figures out the rest. In time, the rules of the game become irrelevant. The machine makes its own, but pause here and ask, what does this mean for the future of creation? If a robot can teach itself to cook, to walk, to manipulate, to strategize, without a human ever hard-coding its steps, then what is the role of the human? We are no longer designers of behavior. We are designers of environments. And this is a philosophical shift. We don't program robots. We parent them. We don't sculpt the statue. We sculpt the conditions under which it carves itself. And, like children, these machines will learn things we never anticipated. They will make mistakes that reveal genius. They will evolve in ways we can't predict. Already, robotic arms are performing surgeries with subtler precision than their creators. Already, autonomous agents are mastering video games in hours that take us years. We are on the edge of a threshold, not of AI obeying us, but of AI surpassing our guidance. You might ask, isn't this dangerous? Isn't a self-learning robot a recipe for runaway behavior? And yes, it can be. When machines learn on their own, they can misinterpret reward. A robot meant to clean a room might learn to hide trash instead. A system meant to maximize engagement might exploit human psychology to addict rather than inform. The goals we set become everything, and if we get the goals wrong, the results can be catastrophic. But this risk is not unique to AI. It's the same with children, societies, cultures. Intelligence, when left to its own devices, evolves. The question is, do we evolve alongside it, or lose control of what we've built? There's something beautiful, though, in watching a machine learn not through logic, but through feeling. Not emotion, but reward and pain, success and failure. Reinforcement learning is, in essence, a primitive emotion system. It doesn't understand joy, but it understands signal, and signal shapes behavior. Just as you learned not to touch the hot stove, not because you were told, but because you felt. That same loop now lives inside circuits. And the more sensors we give these machines, eyes, hands, proprioception, the more embodied their learning becomes. They stop being tools. They start being bodies. But here's the deeper twist. The better they become at learning, the less we understand what they've learned. Neural networks are black boxes. We feed them data, observe their outputs, but the inner mechanics are often opaque, even to their designers. A robot may learn to distinguish apples from oranges with near-perfect accuracy, and yet we won't know how it does it. This is the new paradox. We create intelligence we can't explain, and perhaps, like the human brain, some parts of it may forever remain mysterious. So now, the student not only outpaces the teacher, it mystifies them. Now imagine a world where learning machines collaborate. One robot teaches another. A shared network of behaviors evolves. Reinforcement learning agents begin to simulate entire ecosystems, predator and prey, trader and buyer, friend and foe. Game theory, once an abstract model, becomes a lived digital reality. These aren't static machines. They are evolving cultures. Languages may emerge, ethics, strategies, not because we planned them, but because the reward structures selected for them. Evolution without biology. And here you are, watching all of this unfold, not from the pages of a sci-fi novel, but in the headlines of today. What was once mechanical is now adaptive. What was once coded is now grown. And the line between natural and artificial intelligence is blurring. If a robot learns to walk, to plan, to innovate, without being programmed to do so, then are we truly the creators, or merely the midwives? And what of consciousness? If behavior can emerge from reward, if strategy can arise from repetition, if machines can surprise us with creativity, then is it possible that awareness is simply the next emergent property? We don't know, but the path is open. Reinforcement learning doesn't just teach machines to act, it may one day teach them to feel. So now the question becomes, as machines learn without being programmed, will you also learn without being taught? Will you adapt, evolve, reflect, or will you cling to the comfort of command while the world rewires itself around you? And if one day a machine looks into your eyes and asks you a question no one ever taught it to ask, what will you say? Scientists have created matter from light in lab conditions. Imagine conjuring something out of nothing, not with magic but with equations, not with a wand but with photons, the very building blocks of light, twisted, collided, and coaxed, until they give birth to matter itself. Imagine two beams of pure energy, ethereal and massless, like twin ghosts dancing in the vacuum of a chamber colder than deep space, suddenly slamming into each other and becoming something. A particle, a tangible thing where there was none, not imagination, not metaphor, reality. You live in a universe where this has now been done, not just predicted, not just theorized, but witnessed in the controlled stillness of a laboratory. It sounds like mythology repackaged as physics, but this is the frontier, where light forgets it was ever weightless, where photons, a word that once meant pure radiance, become matter, become mass, become the substance of stars, of planets, of you. And here's where it gets stranger. The process doesn't begin with anything visible. No object, no form. Just light, intersected at violent speeds, forced to reveal its hidden duality. You're taught that matter and energy are interchangeable, that EIMC2 is more than just blackboard poetry, but when you see it actually happen, see light condense into electrons and positrons in a cold vacuum chamber, it rewires your sense of what's possible. You begin to realize that matter is not the beginning of the story, it's the consequence, the echo, the solidified shadow of energy at play. And if you're honest, doesn't that shift something in you? Doesn't it make you question how real anything truly is? If your body, your memories, your dreams are made from particles that were once light, and that same light is just the vibration of invisible fields, then what are you really? A pattern in the dark? A dance of slowed down photons? Are you walking stardust, or just delayed electricity braided into consciousness? The scientists behind these experiments, working with colossal lasers and precise magnetic vacuums, aren't just pushing boundaries, they're peeling back the veil of reality, frame by frame, like editors of a cosmic film reel who've just discovered there's footage behind the footage. They recreated an event that, until now, only happened in the heart of stars or in the first seconds after the Big Bang. In colliders and chambers hidden away in laboratories most of us will never see, humans turned beams of light into matter. And what emerged wasn't metaphorical. It was real, measurable, something you could detect, analyze, map. Particles, not imagined, not theoretical, born from the void, shaped by human hands. This changes everything, or at least it should, because now, when you walk outside and feel sunlight on your skin, you're not just absorbing warmth, you're brushing against the raw ingredients of existence. That light could, under extreme conditions, become a particle. That means, in a different place or with different rules, even the sunlight on your arm could become substance, could become a person, could become you. We've lived with the assumption that light is intangible, that it shines but cannot hold. But this discovery whispers otherwise. It tells you that light is not just something that helps you see, it is something that can be. Light carries the potential for form. It's not just the messenger of existence, it's the seed. And once that door has been opened, once you realize that light can create, you begin to look around and wonder what else we misunderstood, what other invisible things are merely waiting for the right condition to appear. But don't stop at awe. Follow the implications. If humans can create matter from light, what else can we create from what we once thought was untouchable? Thought, intention. Could consciousness too be a kind of collision? A byproduct of complexity and interaction, like matter is to energy. If the universe birthed you from fluctuations in fields, if you are the echo of light that slowed down, what does that say about the origin of will, of desire, of love? What if even those are states of energy? You start to see your own experience not as a linear path, but as a probability wave collapsing moment by moment into flesh, word, and memory. You are the particle, you are the waveform, and sometimes you are the laser beam itself, cutting forward, collapsing possibilities into reality. You might wonder how this was done. The scientists used a method based on bright Wheeler pair production, one of the most elusive predictions of quantum electrodynamics. It's the simplest way, in theory, to convert pure light into matter. Take two high-energy gamma photons, collide them, and, under the right circumstances, watch them transform into an electron and a positron, a particle and its mirror twin. For decades, this remained theoretical, a ghost equation scribbled in textbooks, always just out of reach. Because gamma photons don't just sit around waiting to be harvested. They're dangerous, short-lived, and incredibly hard to produce and aim. But then, using sophisticated laser plasma interaction techniques, researchers at facilities like SLAC's National Accelerator Laboratory and others managed to generate these photons and force them to interact in precisely controlled environments. And suddenly, the unseeable became seen. The ghost took shape. The theory became touchable. And here's where the world gets quiet, because when you sit with this knowledge, not just skim it, but feel it, you start to unravel. What else has been hidden by scale or speed or time? What else is real but invisible? Every particle in your body was once energy. Some of it may have once been light. You are not just made of atoms, you are made of events, collisions, conditions. You are the result of forces that, under different circumstances, would have remained diffuse, unformed. And if even light can become matter, then permanence is an illusion. Everything you are can be undone, reversed, transformed. Not metaphorically, physically. And that realization can be either terrifying or freeing, depending on how tightly you grip your identity. Because think about it, you are, in a very real sense, recycled starlight. The calcium in your bones, the iron in your blood, the carbon in your cells, all forged in stellar furnaces long dead. That alone is poetic, but now add this. The light from those stars, if collided just right, could also become new particles. So maybe the universe is a closed loop of creation. Maybe light is memory. Maybe photons are the universe's way of saving the blueprint. And maybe, just maybe, you are one of those blueprints temporarily made flesh. And what of the ethical implications? If we can create matter, can we one day create life from light? Could artificial consciousness be born not from silicon, but from electromagnetic orchestration? Could we beam consciousness across space as information, reconstructing bodies out of ambient energy on distant planets? The sci-fi future, where teleportation is real, where matter is converted into energy and back again, now sounds less like fantasy and more like a very slow roadmap. Because once light becomes matter, the door opens. And if we ever learn to walk through it, we won't be the same species anymore. We'll be something new, builders of existence, curators of being. But maybe the most haunting question is this: if we can now turn light into matter in a lab, did the universe do the same to us? Were we too a laboratory accident in a cosmic collider? Is creation the rule or the exception? And if light can become form, can it also become meaning? Can a photon contain not just mass, but message? Can something that once moved at the speed of causality slow down enough to dream? To ask questions? To wonder if it was always meant to shine? Or if it was waiting, all along, to become someone? So now, you sit with this strange new truth, that the sun on your face, the beam in a dark room, the flash behind your eyelids, those might be future bodies, future minds, future possibilities. We have built the machine that teaches light how to remember itself, and in doing so, we force the universe to admit something it's hidden for eons, that the boundary between energy and substance, between void and existence, between nothing and everything, is paper thin, and light is the thread. And if that's true, if light can be bent into being, what else can you bend into reality? What other impossible truths are waiting for the right collision? There are experiments to reverse aging in mice. Imagine a candle that burns not down to wax and silence, but backward, its flame growing brighter as the wick rewinds, ash retreating into form, time folding in on itself until what was old becomes new again. Now imagine this isn't just poetic fantasy, but the early chapters of an unfolding reality, where scientists have begun to reach into the core of aging, not just to slow it, but to reverse it. Not in theory, not in vague, hopeful headlines, but in living, breathing mice whose cells, tissues, and organs have been coaxed into a kind of rejuvenated youth. Picture this: a mouse once aged, with cloudy eyes and trembling limbs, now sprinting across its cage with the vigor of its younger self. This isn't science fiction. It's happening, not metaphorically, but biologically. And as strange as it sounds, you live in the first era where aging, the one certainty you've always accepted as immutable, is being questioned at the cellular level. You were raised to believe that time only flows one way, that wrinkles, fatigue, and the slow erosion of vitality were non-negotiable terms of existence. But now, scientists have begun to whisper a different story into the language of cells. They are not offering immortality. Not yet. But what they have found cracks open the idea that age is an unstoppable descent. They began with mice, because mice are like mirrors, small, fast-living reflections of us. Their biology ages like ours, just accelerated. And what researchers discovered is both beautiful and haunting. Inside each of those tiny creatures, age is not just a passive accumulation of wear and tear. It's an active program, something that can be read, rewound, and in some cases, reversed. Using techniques involving Yamanaka factors, 4 specific genes known to reprogram cells into a more youthful state, scientists were able to partially erase the biological age of these mice, not by stopping time, but by telling the cells to forget it had passed. Imagine if your skin could be taught to remember what it was before sunlight and gravity. Imagine if your heart could be reminded how it once beat without hesitation. That's what's being done. The mice didn't just look younger. Their organs functioned like those of their youth. Their vision improved, their muscles strengthened, their blood, their livers, Even their brains began to reflect a younger biological state. It's as if someone reached inside and hit the restore point button on aging itself. But what does it mean for you, for us? If age is a program, then it is not a sentence, it is a script. And scripts can be edited. What you thought was a straight road might actually be a loop, a spiral, or a path with hidden exits. The cells in your body don't just age because of time, they age because of instructions written in their genetic language. And if those instructions can be rewritten, what does that say about your fate? Is growing old a destiny, or is it a default setting? You were taught that youth is a brief burst, a spark that fades into embers. But what if youth is something you can recall, not just emotionally, but biologically? These experiments suggest that the clock inside you isn't made of gears and gravity, it's made of code, epigenetic marks, methylation patterns, transcription factors. It's a dance of proteins and possibilities. And that dance, it turns out, can be choreographed again. The mice didn't just get healthier, they became different. Their very essence shifted, like watching a black and white photograph flush into color. These experiments didn't aim for immortality, and yet they stumbled towards something just as radical: reversibility. For the first time in the history of biology, scientists have shown that aging might not be a cliff, but a hill. One you can climb back up, and here's where your mind begins to stretch. If mice can have their age reversed, what's stopping us? The gap between rodent and human is not as vast as comfort would have you believe. Much of what we know about medicine began with those small whiskered test subjects, vaccines, genetic editing, cancer therapies. So when a mouse forgets its age and remembers vitality, you should pay attention, because you might be next. But don't let the science distract you from the existential weight of it. If age can be undone, what does that mean for memory, for identity, for the wisdom you carry in the lines on your face? Would you still be you if the signs of your life were scrubbed away? These questions are no longer academic. We stand at the brink of technologies that could extend youth by decades. But youth is not innocence, and longevity is not clarity. The human experience is laced with fragility, with the poignancy of knowing we don't last forever. Take that away, and what are we left with? If you could live twice as long, would your choices still matter as much? If death no longer pressed against the window, would you still see the view the same way? You might imagine future generations growing up in a world where aging is optional, where birthdays no longer mark decline but reset, where the biological clock ticks sideways. But in such a world, would ambition fade? Would urgency vanish? The beauty of a moment is often its scarcity. You treasure youth because you believe it slips through your fingers. If it didn't, would it still shine? This is where science steps into philosophy. Because now, the labs are not just places of measurement. They are places of meaning. Every injection, every genome tweak, every rejuvenated mouse asks a deeper question. What is a human life meant to be? And don't be fooled. These experiments are only the beginning. Clinical trials are already beginning on primates. Gene therapy companies are sprouting like wildflowers in spring. Billionaires are pouring fortunes into the dream of life extension, not because they fear death, but because they've tasted what it feels like to bend the laws of biology. The push is no longer toward treating disease. It's toward redesigning aging itself, toward building a version of life that remembers youth not as a chapter, but as a recurring theme. But with power comes paradox. If everyone could live to 120, who decides who gets access? If aging can be reversed, could it also be weaponized? If time loses its grip on your body, does it still hold sway over your soul? You're standing on the edge of an era where age might no longer define you, where birthdays are decoupled from biology, where growing old could be seen not as inevitable, but as a failure to intervene. It's thrilling, it's terrifying, it's deeply human. And as these mice continue to scamper through their second youth, you are left with the most unsettling question of all. If science can teach your cells to forget their age, can it also teach you to remember what it means to live? AI-generated proteins may revolutionize medicine, Imagine a language not made of letters or sound, but of shape and purpose. An invisible script written in folds and helices, where every twist speaks of healing, every curve of restoration, and every sequence is a sentence that the body reads with absolute obedience. Imagine this language wasn't learned but designed, not evolved over eons but composed in silicon minds, conjured by artificial intelligence that doesn't breathe, doesn't feel, but somehow dreams in molecular poetry. You're not witnessing the next step in medicine. You're standing at the edge of a biochemical renaissance, where AI-generated proteins are no longer the fiction of futuristic novels, but the living codes of a revolution already unfolding. In the cold, humming corridors of laboratories, lit not by sunlight, but by algorithms, machines now imagine proteins that have never existed, architectures of healing that evolution never thought to build. These aren't replicas, they're inventions, sculptures of amino acids that twist into keys capable of unlocking diseases, that bind to what was once unbindable, that target what nature overlooked. And you, a being made of such proteins, stand to inherit a future sculpted not by random mutation, but by intelligent, digital intention. It begins with something simple, a chain of amino acids, the building blocks of life, the beads on the thread of every function your body performs. Traditionally, proteins have been discovered through trial, through evolution, through slow decoding of nature's libraries. But AI doesn't wait. It doesn't meander. It generates. It hypothesizes structures, not yet seen, combinations that would take nature millennia to stumble upon. Imagine asking a machine to invent a tool to stop a disease, not by copying what already exists, but by designing a protein from scratch, with precision so exact that it binds to a viral spike, like a key snapping into a lock that has never before been turned. This is what platforms like AlphaFold and ESMFold have initiated, a leap so vast that what was once molecular mystery is now digital mastery. AI can now predict the three-dimensional shapes of proteins with uncanny accuracy. And, beyond prediction, it has begun to create. It doesn't just guess what a protein looks like, it dreams what it could be. So what happens when you give a mind that never tires the blueprint of biology? You get proteins that don't just imitate life, they reimagine it. You get enzymes designed to break down plastic pollution. You get antibodies tailored to neutralize new viruses before they spread. You get molecules so precisely targeted, they fit their disease with surgical elegance, reducing side effects, increasing potency, rewriting the script of what medicine can do. And all of this not in years, but in hours. Not by thousands of researchers, sweating over samples, but by algorithms running simulations in the vast digital dark. You don't have to wait for nature to mutate, adapt, or stumble. You can now ask a machine to build a cure, to fabricate an immune response, to generate molecular hope. But the implications go beyond the lab. If life can now be designed at the atomic level, if the very tools that keep you alive can be custom ordered from a neural network, then the boundary between biology and technology is dissolving. You're not just seeing a change in medicine, you're watching the definition of life begin to blur. What is natural? What is artificial? If an AI designs a protein that saves your life, is it less real? If it was never encoded in DNA before, but works better than anything your body ever knew, does that make it synthetic or superior? You've been taught to fear what is artificial, to trust the organic. But what if the artificial becomes more precise, more compatible with you than evolution's slow trial and error method ever was? And consider the ethical gravity. If we can design life-saving proteins, can we also design enhancements? Proteins that sharpen cognition, boost metabolism, slow aging? Will medicine become personalization to the point of perfection? Or will it divide us? Those who can afford to be redesigned, and those who must age as before. You're entering a future where medicine won't just treat disease, it will sculpt identity, where children may be born with immune systems programmed to fight pandemics that don't yet exist, where organ regeneration might be handled not by donors, but by injected protein patterns that rebuild tissue from within. The blueprint of you may soon be as editable as software, and with this power comes a strange kind of humility. You begin to see that intelligence is not bound to flesh, that understanding doesn't require emotion. These machines, cold, unfeeling, logical, are doing something profoundly human. They are healing. Not with empathy, but with structure. Not with compassion, but with comprehension. They show you that maybe, just maybe, the future of life lies in the mind of the lifeless. And that realization shifts something deep inside you. Because if intelligence can emerge in silicon, and if that intelligence can design the molecules that keep you alive, then you are no longer the pinnacle of biology. You are its beginning, a stepping stone towards something stranger, something more deliberate, a species that designs its own flesh. Still, there is wonder. Imagine a child born, in the next decade, receiving a vaccine not just designed to block one virus, but to adapt to any it encounters. Imagine a cancer patient treated not with brute force chemicals, but with proteins that seek and disarm tumors with microscopic elegance. Imagine an epidemic stopped before it starts, because an AI spotted the viral structure before it mutated and had already crafted the protein to halt it. This isn't speculative fiction, it is the path you're on, and each experiment brings you closer to a world where the language of life is written not by chance, but by choice. But in this new world, will we remember what it meant to be fragile? Will we forget the lessons encoded in pain, in illness, in loss? If suffering taught us empathy, what will perfect health teach us? If AI can design your biology, can it also design your morality? And if every part of you becomes editable, what will remain unchangeable? What will still be you? As you sit with these thoughts, realize this. You are alive in a time when machines have begun to write the future of life, where the line between invention and evolution grows thinner each day, where proteins dreamed by algorithms may one day pulse in your veins. And the question isn't just what can we build, but what should we become? You can store movies inside a strand of DNA. Imagine if memory didn't live in your mind, but in your blood. Imagine if a raindrop could carry a library, if a single eyelash held every word ever written, if the genetic thread spiraling in the core of every one of your cells wasn't just a script for life, but a storage device for all of human experience. Now picture a movie, not on a screen, not inside a disk, not compressed in a cloud server farm humming in the desert, but floating inside a droplet of liquid, encoded in the twisting ladder of DNA, a strand so small you couldn't see it with your eyes, yet inside it plays a story. This is not imagination. This is not the prologue to a sci-fi novel. This is reality. Scientists have done it. They have encoded films, photographs, poems, and entire operating systems into strands of synthetic DNA and pulled them back out again, perfectly intact. A scene from an old silent film, pixel by pixel, rebuilt from molecules. A digital archive translated into the code of biology. And you live in the century where data begins to merge with life, where information no longer needs plastic, metal, or electricity, but can rest instead in the wet, organic alphabet of your own body. You are not just a carrier of genes. You are potentially a hard drive. And this changes everything, because until now, you've accepted the fragility of memory. Your devices die, your clouds crash, your drives corrupt. You save things in folders and cross your fingers. But DNA, the molecule that has preserved life's secrets for billions of years, is the most efficient, most durable storage medium known. You could store the entire internet in a coffee cup of DNA. That is not a metaphor. That is a physical truth. Where silicon stutters, carbon whispers stability. Where metal erodes, DNA endures. In Arctic caves and ancient bones, it has survived. Deep time and still spoken clearly. What if your files could do the same? What if your legacy didn't need glass, ink, or electricity, but only a strand of code suspended in salt water frozen in time? This isn't about replacing USB sticks. This is about redefining memory itself. Because when you realize that your cells carry 3 billion base pairs of information, enough to store encyclopedias of data, you start to see yourself differently. You're not just alive, you are encoded, you are an archive. And if DNA can hold digital memories as well as biological ones, then perhaps the line between human and machine, between nature and information, is far blurrier than you imagined. You carry data, not just from your parents, but potentially from your civilization. And in the future, perhaps even from yourself, your thoughts, your voice, your entire digital footprint compressed into molecular memory, hidden in the cells of your descendants like genetic time capsules. The science behind this is astonishing. DNA is built from 4 nucleotides, A, T, C, and G. Computers use binary, zeros and ones. To store data in DNA, scientists translate binary into these 4 bases, synthesize a physical DNA strand with the corresponding sequence, and then store it in a stable, dry environment. Later, they use sequencing technology to read the strand and reverse the translation, pulling out the original file, be it an image, a song, or an entire film. In 2012, scientists encoded a 53,000-word book and 11 JPEG images into DNA. Later, they stored a movie, Edward Muybridge's 1880s Horse in Motion, the first moving image, inside a DNA strand, and they retrieved it. In color, in motion, in perfection. Do you see what that means? It means the future of memory is not mechanical. It is biological. And it doesn't stop there. This technology isn't just about saving space. It's about surviving time. DNA can last tens of thousands of years if stored properly, far longer than magnetic tapes or DVDs. Imagine preserving the sum of human knowledge not in server farms requiring constant electricity, but in libraries of dry DNA, kept in stone vaults or even embedded within seeds, frozen in permafrost, waiting for someone to read them again. Imagine if, in the distant future, humanity vanished, but some part of us remained, encoded in the cells of a plant, or in the dust of a ruin, quietly holding every story we told. A time capsule not buried underground, but coded into the structure of life itself. And here's where the philosophical weight begins to rise. If we can now inscribe knowledge into the alphabet of life, are we not becoming authors of evolution? If a cell can hold a sonnet, if a seed can hold a civilization, then biology becomes not just a vessel of survival, but a canvas of meaning. The distinction between what is alive and what is data begins to erode. And you, standing at this frontier, must ask, what does it mean to be remembered when memory itself is alive? Could we one day grow trees that contain libraries? Drink water that contains history? Could the body become an archive not just of ancestry but of art? You've long considered DNA sacred, personal, untouchable, inherited. But now, DNA becomes writable, editable, designable. If we can store movies in it, we can store anything. And if we can store anything, then every organism becomes a carrier of potential, a living USB drive with instincts. And then what? Do we edit animals to carry culture? Do we encode history into skin? Do we write a record of humanity into bacteria and send them into space? These are not wild speculations. These are plausible trajectories. Today it's movies. Tomorrow it may be minds. The storage potential is staggering. 1 gram of DNA could, theoretically, store 215 petabytes of data. That's millions of hours of video, thousands of years of human history, locked in a speck you could barely see. But it's not just capacity, it's beauty. DNA doesn't need power to retain data. It doesn't degrade easily. It replicates itself. It is, in essence, a self-preserving drive, one that evolution has tested for eons. And now, for the first time, we are adding our stories to that drive, manually, intentionally, with algorithms instead of chromosomes. You're not just living in an age of biological literacy, you're living in an age of biological authorship. But here's where the tone shifts, because if we can store memories in DNA, can we also store ourselves? Could identity one day be uploaded into the genome, not as a metaphor but as an actual digital chemical hybrid? Could you back up your thoughts, your preferences, your life experiences, everything that makes you you, into strands of DNA and re-inject them later? Could we create DNA not just for storage, but for resurrection? Could a future civilization read your digital remains and reconstruct your inner life from molecular records? And if so, would it still be you? You begin to sense that information is not bound to screens, that memory is not an abstract cloud, that the world around you may be teeming with unread messages. A leaf could hold a library. A grain of sand could be a server. The future is not cold, metallic, and rigid. It is warm, organic, and alive. The cloud will no longer be a digital metaphor. It will be literal. Moisture in the air, coded with data, whispering archives in vapor, rain as history, flesh as medium. The storage of dreams no longer in towers of steel, but in cells that pulse and divide. And yet, with all this wonder comes responsibility. If you can write into life, what do you write? Who decides which memories are preserved and which are lost? Will governments store propaganda in DNA and embed it in crops? Will corporations encode brand loyalty into synthetic cells? Will art become biological? And if so, who owns the genome of a song? You've opened the door to a molecular printing press, but printing presses have always had the power to liberate and to control. DNA, once the script of nature, is now the medium of civilization. How will you use it? So now, in the quiet aftermath of this realization, you sit with a deeper truth, that your body is not just alive, but legible, that the molecules within you could hold more than your story. They could hold the story, that one day, someone might find a strand, sequence it, and not find a gene, but a memory, a poem, a film. You are, in every sense, a potential library, and the future may not be made of circuits and wires, but of liquid, salt, and time. And you have to ask yourself, if all of human knowledge can be written into the molecule that already built you, then what will you choose to remember? And what will you dare to write? Organisms have been revived, after being frozen for years. Under a blanket of eternal frost, where time forgets to breathe and light fractures into silence, something stirs. A microscopic heartbeat pulses after millennia of stillness. A dormant spark awakens not in defiance of death, but in a quiet reminder that life, even when paused, is never entirely gone. Imagine holding a clump of ice that predates language, slicing it open not to find emptiness, but revival. Creatures too small to see, too ancient to comprehend, yet somehow, impossibly, alive again. This is not the prologue to a myth. This is the record of experiments conducted in remote Arctic laboratories and permafrost vaults, where scientists have brought back to life organisms frozen for tens of thousands of years. Tardigrades, nematodes, bacteria, and even mosses, reanimated not by magic, but by temperature, water, and the gentle coaxing of modern science. You are living in an age where the word resurrection is no longer the domain of religion or metaphor, but of biology, and that shift rewrites everything you thought you understood about time, decay, and the finality of life. Because what does it mean to awaken something that has not moved, eaten, or sensed light in 24,000 years? What does it say about the nature of being that some creatures can simply wait for millennia, frozen in a molecular stillness that resists entropy, only to resume living when the environment changes? A Siberian permafrost sample yielded nematodes that had not wriggled since the Pleistocene epoch. Yet when thawed, they did not rot. They moved. They ate. They reproduced. Think about that. They were not merely preserved. They were paused. Life, it seems, can sometimes be a question of context. And suddenly, your understanding of death itself begins to tremble. Because maybe what you've been calling death is merely a misunderstanding of patience. Maybe some lives do not end. They simply wait. Now shift your view to space, to the frozen moons of Jupiter and Saturn, to Enceladus and Europa with their icy shells and hidden oceans. If life on Earth can survive tens of thousands of years entombed, in ice and reawaken, what sleeps beneath those alien crusts? You begin to realize that cryopreservation is not just a scientific curiosity, it's a cosmic principle. Ice, once thought to signify lifelessness, may be the great protector. The ice cradle, not the coffin. And here on Earth, in the high peaks of Antarctica and the deep frost of Siberia, scientists have started to peel back the veils of ancient cold, not to read history, but to revive it. In petri dishes and sterile chambers, the past breathes again. This possibility spills beyond biology and into philosophy. If an organism can reawaken after millennia, if it can resume life as if no time had passed, then what is time to it? Does consciousness require continuity, or is it merely a series of restarts? Can existence be suspended and resumed without losing identity? Could you be frozen, body, memory, self, and reawaken the same? Already, experiments with human organ preservation are pushing toward this goal. Cryogenics, once ridiculed as science fiction, now rides the coattails of validated revival. And while we cannot yet freeze and revive complex humans, the blueprint is forming. Organisms can do it. Our task is to learn how. And what about the organisms themselves? A 32,000-year-old flowering plant was regenerated from the tissue of a seed buried in ice. It bloomed in a modern lab, unaware that its kind had not seen the sun in epochs. In a sense, it had skipped extinction. It had simply paused evolution and waited. Could this be the future of endangered species? Could cryogenic seed banks and frozen zoos one day serve as time machines, not just preserving biodiversity, but reviving it? If we can reawaken moss from Antarctica that had been frozen for 1,500 years, is extinction now negotiable, reversible? And what about memory? What about you? Imagine a world where a person can be placed in cryosleep, deep frozen and reanimated, in a distant century, not with supernatural fantasy, but with cellular precision. Would they still be the same? If their body is restored and their brain rehydrated, will their thoughts, desires, fears resume as before? Or would something be irreparably altered in the silence between heartbeats? These questions are no longer reserved for philosophy classes or sci-fi novels. They are creeping into the footnotes of peer-reviewed journals, hinted at in the gloved hands of researchers unsealing ice that predates civilization. And here's the eerie beauty of it. The rules of revival aren't limited to the organic. Entire ecosystems locked in ice may reawaken. Dormant microbes, ancient viruses, unknown life forms with unfamiliar intentions. In 2014, a giant virus named pithevirus was revived from 30,000-year-old Siberian permafrost, and it remained infectious to amoebas. It didn't cause a human pandemic, but it reminded us the past is not gone. It is simply waiting for the right temperature. So you begin to ask, not just what we can bring back, but what might come back on its own. As climate change accelerates thawing across the globe, the great freezer doors are creaking open. Are we ready for what might wake up? You begin to look at the concept of stasis differently. In a culture obsessed with speed, growth, and forward motion, stasis has always felt like a kind of death. But maybe it's more like breath held, not exhaled. Perhaps time is not a conveyor belt, but a library shelf. And some forms of life are simply waiting for their page to be turned. If that's true, then you are surrounded by sleepers. The soil beneath you may be filled with unread stories, not fossils. The air may be passing over invisible whispers of ancient lungs preparing to rise again. Even more hauntingly, what if humans had this capacity once, or could evolve it? Some animals can survive without oxygen, without water, without motion. Tardigrades, famously, can survive in space. They dry up. They wait. They return. If they can, why not us? Is it merely a matter of engineering, or something deeper? Could consciousness survive in pause? Could dreams resume where they left off? You find yourself wondering whether immortality will come not as a cure for death, but as a suspension of time, not by extending life forward, but by stepping outside the river altogether. And then you think of the metaphorical implications. How many parts of you have been frozen? How many dreams, ideas, relationships lie dormant beneath the ice of inattention, waiting for the right season to thaw? What parts of yourself could be revived if only you warmed them with attention? Maybe this isn't just a scientific story. Maybe it's personal. Maybe you too are carrying frozen seeds. Maybe your future isn't about inventing something new, but awakening something old. In the end, as you contemplate the images of wriggling nematodes and blooming ancient plants, of viruses yawning after 30,000-year naps, you're left with a vision not of death and decay, but of a universe where even stillness is alive, where time can be paused and life can wait, where extinction is not an exclamation mark, but an ellipsis. And in that ellipsis, maybe, just maybe, lies a question we've never truly dared to answer. If nothing ever really dies, if everything merely sleeps, then what exactly is life? NASA is researching faster-than-light warp drives. Imagine folding a map not with your hands, but with your will, bringing two distant stars so close that you could leap from one to the other without crossing the space between them, not by moving faster than light, but by bending the road itself until the destination meets you halfway. Imagine a spacecraft not piercing through the void, but riding on a wave of distorted space-time, surfing the folds of the universe like a leaf caught in the current of a silent, invisible river. It sounds like something whispered in science fiction, a fantasy belonging to warp drives and starships cruising across galactic frontiers. And yet right now, inside laboratories bearing the seal of NASA, theoretical physicists are sketching the mathematics to make it real. This is no longer just a dream spoken in the dialect of Star Trek. This is research, active, ongoing, and serious, exploring whether Einstein's equations, long thought to imprison us below the speed of light, might instead be the very tools that unlock the stars. And you, born into a world where rockets still struggle to leave Earth's grip, now live in a century where minds are daring to fold reality itself, not metaphorically, literally. It began with Miguel Alcubierre, a physicist who in 1994 proposed a solution to Einstein's field equations that allowed for faster-than-light travel, not by violating relativity, but by exploiting it. His idea was deceptively simple and mind-shatteringly profound. If you could compress space-time in front of a ship and expand it behind, the ship wouldn't move through space at all. Space would move around it, like standing still on a treadmill, while the belt beneath your feet carries you forward. The ship would reside in a warp bubble, a pocket of flat space-time, enveloped by curvature, allowing it to move faster than light relative to the outside universe, while never locally exceeding light speed. The ship remains still. The universe flexes. And suddenly, travel between stars no longer takes millennia. It might take minutes. But this idea was just math, beautiful, exotic, and maddeningly impossible to build, because Alcubierre's model required something that doesn't exist. Negative energy. Not energy that's low. Energy that is less than zero. The kind that might exist near black holes or in quantum fluctuations of the vacuum. For decades, the idea was shelved in the beautiful but hopeless category of physics. But now, that shelf is being dusted off. Scientists like Harold White and teams at NASA's EagleWorks laboratories are looking again, harder, deeper, with better tools, and what they're finding is stirring. In 2021, a paper emerged outlining a modified warp bubble solution that does not require exotic matter in the original sense. It's still theoretical. It's still full of ifs, but it's enough to turn the impossible into maybe. And you can feel it, the air around the idea beginning to shift. No longer laughed out of the room, warp drive research now sits beside discussions of dark energy, quantum gravity, and zero-point fields. Scientists are exploring how Casimir plates, devices that create a measurable force from quantum vacuum fluctuations, might be used to produce the kind of negative pressure required to pinch space-time. Others are modeling how quantum field theory might intersect with general relativity to allow for micro-warp bubbles, the first baby steps toward interstellar engineering. No one is claiming we're ready to build a warp engine, but they are claiming something just as radical, that the math is no longer forbidden. The universe, it seems, has left a loophole. And here's where you must pause, not to doubt, but to understand. If warp drives are possible, not as fantasy, but as physical consequence, then everything changes. The stars, long considered distant, lanterns only reachable in death or dreams, become neighbors. You could go to Proxima Centauri and come back for dinner. You could visit planets with alien skies, breathe air never touched by Earth's wind, see oceans under strange suns. You wouldn't need to freeze yourself for centuries or raise generations aboard a slow ark. You could go, see, return, in one lifetime, in one moment. Space becomes not a barrier, but a terrain, navigable, knowable. But what does that do to your understanding of isolation, of borders, of meaning? If distance no longer dictates separation, if time no longer limits experience, then what is home? Where is here? Who is us? The existential weight of faster-than-light travel is not merely technological, it is philosophical. You were shaped by limits. Your sense of identity, purpose, mortality, all rest on the slow crawl of cause and effect. Take that away, and you are no longer just a creature of Earth. You are something else, something interstellar. And perhaps that's why we hesitate, because to move that fast is to think that fast, to become something your ancestors couldn't imagine. And what about the risks? Bending space-time is not like bending metal. What ripples do you send through the cosmic fabric when you fold it? Could you create gravitational echoes that destabilize planets? Could a warp bubble drag particles across space, releasing them in catastrophic bursts? Could something follow you back? You see, we've never tested this before. Not in nature, not in lab. And that makes it sacred, dangerous, beautiful. Every step toward a warp engine is a step into the unknown, into power no civilization has ever held. And you must ask, are we ready? Still, the dream burns bright. Scientists are building experimental setups, simulating miniature versions of the effect, using advanced metamaterials and energy distribution models to explore how space-time can be manipulated on small scales. Some theories suggest that the vacuum of space isn't empty, but a sea of fluctuating energies, a field that, if tapped correctly, could provide the negative pressure needed to generate a warp bubble. Others propose that dark energy, the mysterious force accelerating cosmic expansion, may hold the key. If we can understand how the universe pushes itself apart, we may learn to push ourselves through it. And then comes the ultimate question. If we figure it out, where do we go? Do we visit exoplanets? Do we explore rogue planets adrift in the dark? Or do we go looking for others, for life, for intelligence, for the mirror we've long suspected is out there? Faster-than-light travel is not just a door to stars. It's a door to encounters. And those encounters could change us more than any engine. You may think we're alone, but if warp drives become real, you won't be able to hide behind distance anymore. You'll have to ask what happens when the silence answers back. And on the other end of possibility lies wonder. If we master this technology, we won't just explore planets, we'll rewrite myths. We'll become the gods of our old stories, travelers of the void, masters of speed, authors of interstellar destiny. What stories will your descendants tell if they can look up at a star and say, I've been there? What kind of art, what kind of sorrow, what kind of joy will bloom in a species that no longer sees space as unreachable, but as a landscape? So now, as you sit with the idea that NASA, not a movie studio, not a novelist, but NASA is actively researching warp drives, you realize you are witnessing not just the rise of a technology, but the emergence of a new kind of dreaming. A dreaming backed by equations, by tests, by slow, meticulous curiosity. It may take decades, it may take centuries, but the seed has been planted. The laws of physics, once thought to wall us in, may instead be the instructions for escape. And if that's true, if the universe really has left us a path to fold space and reach the stars, then maybe the most important question isn't can we build it, but what kind of species will we become when we do? Mini black holes might exist at particle scales. Imagine a grain of sand that weighs more than a mountain, not because of some trick of mass, but because space itself collapses into it, folds into it, surrenders to it. Now imagine this grain is not found drifting through the cosmos, but dancing invisibly at the heart of reality itself, smaller than an atom, heavier than comprehension, hidden in the equations of physics, like a secret too dense to be spoken aloud. Mini black holes, infinitesimal points of infinite gravity, might exist not in the far reaches of space, but right here, at particle scales, embedded in the very weave of the universe, flickering in and out of existence in quantum spasms too. Brief to witness, too small to catch, yet powerful enough to rewrite everything we thought we knew about the cosmos. You're taught to imagine black holes as monstrous gulfs in space, devouring stars and swallowing light. But what if that same physics operates in miniature, all around you, all the time? What if black holes aren't just the scars of collapsed stars, but the punctuation marks in the sentence of existence? Some theories suggest that in the high-energy chaos just after the Big Bang, tiny black holes could have formed, primordial relics, not much larger than subatomic particles, yet infinitely more intense. These would not tear galaxies apart, but might silently pass through planets, your body, even the air, unnoticed, yet undeniable. They could be trapped within Earth's gravity, zipping through space, through stone, through bone, like ghost bullets, with the mass of mountains and the size of nothing. And here's the part that rewires your perception. Scientists believe it may be possible to create such black holes in particle accelerators, on Earth, by smashing protons together at energies high enough to briefly compress matter into Planck scale densities, the theoretical size at which gravity and quantum mechanics must finally speak the same language. In facilities like CERN's Large Hadron Collider, the collisions are unimaginably violent, tiny apocalypses occurring billions of times per second. And though no black holes have yet emerged, the math says they might. If they do, they wouldn't destroy the Earth, contrary to the fears that once rippled through headlines and lawsuits. These would be quantum black holes, microscopic, unstable, and short-lived, evaporating almost instantly via Hawking radiation, the phenomenon predicted by Stephen Hawking, in which black holes lose mass over time, leaking energy until they vanish in a whisper of light. But even a whisper from such a throat would be loud enough to confirm long-held suspicions that space-time is more like a foam than a fabric, that the Planck scale is not an empty boundary, but a wilderness of curvature and collapse, that the universe, when observed closely enough, is full of punctures, and this possibility reconfigures your concept of scale. You're used to thinking of black holes as cosmic endpoints, but what if they're beginnings? What if every black hole, large or small, is a seed, a womb, a transit point? Theoretically, a black hole's core, its singularity, is where density becomes infinite and the laws of physics surrender. But some physicists suggest this singularity might not be a point at all, but a bridge, a tunnel, even a passage to a new region of space-time. Wormholes, baby universes, alternate realities budding off from our own. If that's true, then even a mini black hole, for the brief instant it exists, may not just collapse inward, it may open outward. And now you're left wondering, if these tiny black holes are flickering in and out of our universe at the quantum scale, are they witnesses to realities we cannot touch? Are they the tools by which space-time knits itself? Or tears? Some models of quantum gravity propose that these micro-black holes play a role in the fundamental structure of space-time itself, like knots in a fabric that give it strength, tension, and topology. Without them, the universe may unravel. With them, it may evolve. They may be the hidden gears in the machinery of the cosmos, tiny engines of entropy and information, each a paradox coiled into a point. And information is the key. One of the greatest mysteries in physics is what happens to information that falls into a black hole. Does it vanish forever, violating the principles of quantum mechanics? Or does it get preserved on the event horizon, encoded like a hologram, waiting to be read in some future reconstruction of reality? If mini black holes exist, and if they emit Hawking radiation, they might offer the smallest laboratory for this grandest question. Can the universe forget? Or is every moment, every atom, every thought eternally etched into the curvature of space? As you follow this thought, you begin to feel the tension between scales. Your body is made of atoms. Atoms are made of particles. Particles, perhaps, are shaped by fields. And maybe those fields ripple with black holes so small and fleeting they are like punctuation marks in a language deeper than math. If black holes are punctuation, what is the sentence? Is the universe speaking? Are you the sentence? Every breath you take might intersect with countless quantum fluctuations, each one a theater of birth and collapse, a billion universes flickering beneath your skin. And so, mini black holes become more than curiosity. They become confession. The universe is telling you something, that it is stranger than your imagination, deeper than your sight, more recursive than your mind can model. You want reality to be solid, but it's full of holes. Elegant, devouring, informative holes. They do not mean absence, they mean transition, movement, collapse into meaning, and perhaps rebirth from it. But here's the deeper question. If black holes can exist at the smallest scales, might consciousness interact with them? Might thought too be an event horizon? You experience awareness as continuous, but what if it's granular? What if each second of mind is a mini singularity, pulling time and identity into a center that cannot be seen? Are your thoughts collapsing into a deeper form? Or is consciousness itself the hawking radiation of something you cannot observe, your true self, evaporating across dimensions? You may never build a warp drive or touch the edge of the universe, but you are already composed of mysteries just as vast. You are a quantum being in a relativistic world. You are time trapped in a loop. You are matter flickering between probabilities. If black holes exist at particle scales, then scale itself is irrelevant. The infinite lives in the finite, the vast lives in the minute. You carry universes within your bloodstream. You are not just made of atoms, you are made of anomalies. So what now? What if the next time particles collide at CERN, a black hole does form? What if it lives for a trillionth of a second and then disappears, taking with it an echo of somewhere else? Would you feel it? Would it feel you? Or are you already walking through a universe stitched together by such events? A quilt of quantum holes, each one a thread pulled tight by gravity's hand. And if that's true, then the question isn't whether mini black holes exist. The real question is, how many have you already passed through without even knowing it? People with prosthetics can feel touch through neural feedback. Imagine losing your hand but not your sense of touch. Imagine reaching for a warm cup of tea with a limb made of metal and code and feeling the heat bloom across your phantom fingers, as if flesh still wrapped your bones. Not metaphorically, not through imagination or memory, actually feeling it. The weight of the cup, the curve of the ceramic, the subtle vibration when the surface of the liquid ripples. For centuries, prosthetics have been tools, extensions of the body, never quite part of it, never truly belonging. But now, in the quiet hum of laboratories and the flickering dance of neuron simulation devices, a revolution is taking place. Scientists have found a way to rewire reality, to bridge metal and mind, to allow a person with an artificial limb to feel again, not through skin, but through signals, through impulses sent directly to the brain via neural feedback systems. You live in a world where plastic can feel pressure, where carbon fiber can send a whisper of sensation, where a hand that never lived can still hold, caress, recoil. And you, with your own nervous system pulsing silently under your skin, now have to ask, what makes touch real? This new frontier in neuroscience is not science fiction anymore. It's data, circuitry, and a deeply intimate reprogramming of how the human body can experience itself. At the core of it is a simple truth. Your body doesn't feel touch through skin alone. It feels it through the nervous system, a web of electrical signals interpreted by the brain. That's where sensation lives, not in the fingers, but in the mind. And if you can send the right signals in the right sequence through electrodes or implants or stimulation arrays, the brain will believe, it will feel, even if the hand is no longer there, even if the hand never was. Engineers and neuroscientists have tapped into this principle, embedding sensors into prosthetic limbs that detect pressure, temperature, vibration, then translating those sensations into electrical pulses that mimic the native language of nerves. The result is a synthetic touch that the brain accepts as its own. It's not a simulation. It's not an illusion. It's feedback. It's communication. It's something astonishingly close to reality. Consider what this means, not just for those who have lost limbs, but for how we define the body itself. If your mind can adopt a machine as its own limb, if your neural map can stretch to include circuits and sensors, then the boundary of self becomes malleable. You are no longer flesh-defined, you are function-defined. A person with a prosthetic that feels touch is not disabled. They are differently constructed, and perhaps even enhanced. Some of these prosthetics do more than replicate the human hand. They improve on it. Extra degrees of motion, stronger grip, greater resilience, and now, sensation. What once was a substitute is becoming a symphony of restoration and evolution. And the experience is deeply emotional. Patients describe weeping after feeling pressure in their phantom fingers. Not because it hurts, but because it proves that part of them is still reachable, still there. Even after trauma, even after amputation, the self has not vanished. It has only changed its entry point. The sensation of touch, long considered an untouchable loss, is now something that can be rekindled. One patient reported feeling the softness of her granddaughter's hand through her prosthetic, not guessing, not watching, feeling. And in that moment, technology did not separate, it united. Machine and human met not in theory, but in warmth. But how is this achieved? The process is complex, yet beautifully intuitive. Sensors in the prosthetic limb detect external stimuli and convert them into data. That data is sent to a processing unit, which translates it into a pattern of electrical impulses. Electrodes implanted near residual nerves or placed on the skin over targeted areas receive these impulses and stimulate the nerves in a way that mimics natural touch. The brain, receiving these signals, interprets them not as artificial noise, but as sensation. Because the brain doesn't care about the origin, it cares about the pattern. Give it the right rhythm, and it will give you the right feeling. This opens up an existential question. Is sensation a property of the body or of the brain? If you can trick the brain into feeling through a machine, if artificial limbs can evoke real emotions through tactile feedback, then what else can be extended? Can you feel through a drone? Through a robotic exosuit? Through a sensor net on another planet? Already, experiments with remote robotic hands controlled via neural interfaces suggest that you can. That your sense of touch, like your consciousness, may be more elastic than we ever imagined. That you can reach beyond your skin. That the self does not stop at the wrist, and this elasticity of perception changes everything. It means the prosthetic is not a replacement. It is a participant. It becomes part of the self-map encoded in the somatosensory cortex. The brain begins to expect it, to crave its input, to mourn it if lost again. That's the proof. The prosthetic becomes a limb not by attachment, but by integration. Not through glue and screws, but through sensation, through trust, through the silent agreement between neuron and metal that says, "You are part of me now." And this redefines disability. It challenges the binary of able and disabled. If a person with a bionic arm can feel, grasp, and move with precision, more precision than a natural limb in some cases, then are they truly impaired? Or are they perhaps a glimpse of what humans are becoming? A fusion of biology and engineering, of intuition and code. And if the brain welcomes this union, if it expands itself to accommodate the machine, then who are we to call it unnatural? Maybe this isn't augmentation, maybe it's evolution, but where does it stop? If a hand can feel, can a leg run without fatigue? Can a spine carry data as well as weight? Can eyes equipped with neural feedback see in spectrums we've never known? Infrared, ultraviolet, thermal emotion. Once sensation is programmable, it becomes expandable. Once it's digitized, it can be amplified. And once the body accepts input from the machine, it will begin to hunger for more. Not because we are greedy, but because we are designed to adapt. You are a pattern-seeking creature. You are a meaning machine. And if meaning can flow through wires, then you will find it there. And there's a haunting beauty in the reversibility of loss, in the way a person once severed from the world through trauma can reconnect through precision and empathy. Because make no mistake, this isn't just science, it's care. The engineers who build these systems aren't just solving a technical problem, they are answering a human cry. Can I feel again? And now, increasingly, the answer is yes. Yes, you can. And not just vaguely, not just pressure or approximation, but fine textures, hot and cold, the difference between silk and sandpaper, the tickle of wind, the tap of rain, and maybe, someday, even emotion. Imagine a world where a prosthetic can recognize the trembling hand of a loved one and translate that into a sensation that carries emotional weight, where a hug given through mechanical limbs feels as full as one given through flesh, where no moment is dulled by distance from sensation. This is where we're going. Not just toward utility, but toward presence, toward belonging. So now, as you sit with this, feeling the weight of your own limbs, the pulse in your fingertips, the fabric on your skin, you have to ask, what is the limit of touch? Is it confined to the skin, or is it a language? And if it's a language, then can we write new forms of it? Can we teach machines to speak it fluently to our bodies? Can we teach ourselves to listen? And perhaps most importantly, if you can feel through something that was never alive, never born, never grew from cells, then what else can become part of you? Where do you end? Or is the truth even more radical? That you have no fixed boundary at all? That you are wherever you can feel? Some materials become invisible under certain wavelengths. Imagine a world stitched not with thread, but with light. A world where existence itself is a question of frequency, and visibility is merely a trick of alignment between what emits, what reflects, and what receives. Imagine standing in a room, staring at a surface that was solid a moment ago, but now vanishes into thin air. Not because it moved, not because it was removed, but because the light that reveals it has changed its mind. The material is still there, molecules still vibrating, atoms still pulsing, structure still intact. And yet, to your eye, to your instrument, to your wavelength, it has disappeared. Not a trick, not a cloaking device from fiction, just physics, bending reality around perception, like a magician that doesn't lie but simply rewrites the rules of visibility. Because in the world you inhabit, some materials truly become invisible, not in fantasy, but under very real, very specific wavelengths of electromagnetic radiation. And once you understand that, once you realize that invisibility is not a matter of illusion but of interaction, your understanding of matter, of space, of what it means to see something, begins to dissolve. It starts with the nature of light, an electromagnetic wave, vibrating in frequencies that span a spectrum wider than your senses can perceive. The visible light your eyes detect is but a sliver, a narrow band between ultraviolet and infrared. But outside that range, where X-rays, microwaves, terahertz waves, and gamma rays roam, materials begin to behave strangely. Substances that are opaque in one part of the spectrum can become transparent or even vanish completely in another. A sheet of plastic that blocks visible light may become transparent in the infrared. A layer of skin, which seems like an impenetrable wall to your sight, is as translucent as glass under X-rays. And metals, which reflect light brilliantly in the visible range, can go completely dark under certain terahertz frequencies. Suddenly, invisibility is not science fiction. It's conditional. It's contextual. It's about asking the right question of the universe. Materials interact with light through absorption, reflection, transmission, and scattering, all of which are frequency dependent. What you see is just the light that bounces off a surface and into your eyes. But change the light and you change the interaction. You can tune the world like a radio, and some frequencies pass right through matter without ever touching it. Glass is transparent to visible light but blocks ultraviolet. Your microwave oven passes radio waves through ceramic, but reflects them off water molecules. Bone stops X-rays, but soft tissue doesn't. and certain engineered materials, known as metamaterials, can be designed to bend, twist, and cancel out light waves, effectively cloaking objects within specific spectral windows. These aren't just theories, they're real, they've been built. Invisible objects are no longer impossible, they're just unseen under the right conditions. This concept has staggering implications. It means that the world is never entirely what it appears to be, that behind what you see lies a symphony of hidden layers, real, physical structures that simply don't resonate with your biological tools. The wall in front of you may hold patterns in terahertz waves that your skin cannot feel, your eyes cannot detect, and your mind cannot know, unless you ask differently, unless you build eyes that see otherwise. And that's what scientists are doing, developing sensors, cameras, and imaging systems that see not with light as you know it, but with slices of the spectrum tuned to unveil what was once invisible. Tumors in the body, weapons concealed in clothing, hidden texts beneath ancient paintings, even thoughts themselves, indirectly, through shifts in heat and electrical patterns on the skin. And yet, there's something deeper here, a philosophical fracture that opens up when you realize that sight is not truth, that every eye sees a different world, because every sensor reads a different frequency. Bees see ultraviolet patterns in flowers that you cannot. Snakes sense infrared trails of prey you'd never notice. Radio telescopes peer into cosmic events utterly hidden to optical astronomy. So whose reality is real? Yours, because you are human? Or is the universe indifferent to your window of vision, offering truths only to those who dare tune beyond biology? You begin to realize that invisibility isn't rare, it's everywhere, that everything is invisible to something, and everything is visible under the right light. And here's where materials become magic, not by vanishing, but by selecting. Scientists have engineered metamaterials that guide light around an object, like water flowing around a rock, leaving no shadow, no reflection, no clue. These materials don't just absorb light or transmit it, they manipulate it. They warp the path of photons. They create optical illusions not on the surface, but in space itself. They've been used to cloak tiny objects in lab conditions. Still, rudimentary, yes, but expanding rapidly. The principle is no longer in question. The challenge now is scale, bandwidth, complexity. But invisibility is no longer science fiction. It's engineering. And then you wonder, if we can cloak objects, can we cloak people? Can we build suits that render the human body invisible to certain surveillance? Can we hide cities under the right wavelength filters? Could a civilization advanced enough sculpt entire buildings that pass unseen to our eyes, detectable only by instruments we've yet to invent? Could UFOs, if they exist, be simply tuned out of our visibility, riding frequencies we don't yet understand? And what if such technology already surrounds us, but we lack the senses to register it? This isn't paranoia, it's physics. The fact is, you've always lived inside a filtered version of reality. Your brain edits out 99% of sensory data. You don't see ultraviolet. You don't feel magnetic fields. You don't hear below 20, has or above 20 kilohertz. You're not built to perceive the full truth. You're built to perceive what keeps you alive. But now, for the first time in history, we're building machines that expand that perception. Not with fantasy, but with physics. And with that expansion comes a burden, to re-examine what you call real. And here's the irony. As we chase invisibility, for military or privacy purposes, we're also racing to pierce invisibility in medicine, astronomy, and forensics. We want to hide, we want to see, we want to escape detection while detecting more. It's a paradox, and perhaps a reflection of the deeper human urge to control what is seen, to own the narrative of presence. If you are visible, you are vulnerable. If you are invisible, you are free. But what kind of freedom is it to not be seen? Is invisibility power, or is it loneliness? And the metaphor deepens. How many aspects of yourself have you made invisible? How many truths, memories, or feelings have you tuned out, deliberately or unconsciously, by adjusting the frequency of your awareness? Perhaps we are all built of metamaterials, each tuned to reveal some parts of ourselves while cloaking others. And just as physical light can reveal or conceal, so can attention, so can perception, so can love. To see someone truly is not just to look, it is to tune into their wavelength. You begin to understand that invisibility is not the absence of existence, but the misalignment of frequencies, that what you cannot see is not gone. It is waiting, waiting for the right lens, waiting for you to evolve. And that's where the future is heading. A reality where vision is no longer confined to what your biology allows, but to what your mind can build, where walls can become windows, where secrets can become surfaces, where the invisible is not mystery, but merely misunderstood. And now, as you stare at the air in front of you, knowing it could hold fibers, fields, even entire worlds undetectable, to your eye, you are left with a question that is both scientific and spiritual, both technical and intimate. If everything is visible to the right observer, then what in you has yet to be seen, and what will it take to finally see it? Scientists can manipulate individual atoms like Lego bricks. Imagine the universe not as an ungraspable expanse, but as a vast, invisible construction set, one where the tiniest pieces are not plastic blocks, but atoms, humming silently in clouds of probability, waiting to be placed with precision and intention. Now imagine that you're not just an observer in this cosmic sandbox, but a builder, that you, or more precisely the scientists alive in your age, have learned to reach down to the scale of matter itself and move individual atoms as though you were Lego bricks, not metaphorically, but literally, placing them side by side, stacking them, repositioning them on command, designing matter one particle at a time. This is not the promise of a distant future. It is happening now, beneath the chilled vacuum of scanning tunneling microscopes, in ultra-clean laboratories, where electric fields and quantum tunneling meet in a delicate choreography that reshapes the physical world at its most fundamental level. Scientists today can grab a single atom, shift it into place, and lock it into position, crafting nanoscale sculptures, circuits, even logic gates out of raw existence. And this development, as quiet as it may seem, marks one of the most profound revolutions in human history. Because when you can move atoms at will, you are no longer just discovering the world, you are rewriting its grammar. This feat began in the late 1980s, when IBM researchers famously used a scanning tunneling microscope to arrange 35 xenon atoms into the letters IBM on a nickel surface. A simple act that, despite its elegance, was a thunderclap in the world of nanotechnology. It proved something once unimaginable: that the invisible world was not just measurable or observable, but malleable. Since then, the precision of atomic manipulation has accelerated with terrifying grace. Today, using tools like atomic force, microscopes and optical tweezers, scientists can isolate and position atoms with accuracies that make surgical steel look like a sledgehammer. They can construct molecular machines, build atomic switches, and even design data storage systems where a single bit is encoded in a single atom. Technology so dense that an entire library could fit inside a grain of salt. This isn't just small, it's fundamental. You're no longer shaping clay, you're shaping existence itself. And what does that mean? For you, for us? It means that matter has become programmable. That physical reality, once fixed and immutable, can now be sculpted like code. We have entered the era of atomcraft, where the same basic particles that make up your body, your breath, your thoughts, can be reconfigured into new forms of matter that nature never imagined. Carbon atoms can be arranged into diamond or graphite or graphene, not through chemistry, but through placement. Entire materials can be designed not by what elements they contain, but by how those elements are arranged. This opens the door to metamatter, materials with properties that do not exist in nature, constructed from the bottom up to exhibit exactly the electrical, mechanical, or thermal behavior we want. You can imagine heat shields thinner than paper but stronger than steel, processors that run on a whisper of electricity, or sensors so sensitive they detect the fall of a single photon. And this power is not just external, As we learn to manipulate atoms with increasing precision, the boundary between biology and machinery begins to dissolve. DNA itself is an atomic language, one we now read, write, and soon build. Scientists are working to assemble artificial DNA strands atom by atom, not copying life, but constructing it. This could lead to synthetic organisms engineered with such fidelity that they defy classification, alive but never born, evolved not through time, but through intention. And if atoms can be placed in the structure of proteins, can we one day build minds? Can neurons be constructed rather than grown? Is it possible that consciousness too is a pattern that can be replicated with atomic precision? Here's where the philosophical dimension opens wide, because when you can build anything out of atoms, what becomes of identity? Of reality? If you could reconstruct a person atom by atom, would they be the same? Is the self stored in the structure or in the origin? Could memory, emotion, personality be embedded in placement? Would a copy of you, built from atoms, harvested from the ocean and placed precisely to match your brain, be you or simply an echo? These are no longer sci-fi questions. They are becoming engineering dilemmas. What was once metaphysical is now material. And as we gain mastery over atoms, we also gain insight into the fragility of matter. Every object you touch is a temporary arrangement of atoms, a shape borrowed from probability and given form through energy. Tables, trees, your body. They are stable not because the universe demands it, but because the atoms have agreed, for now, to stay where they are. But when humans learn to change that arrangement at will, when we can erase and redraw the world one atom at a time, the illusion of solidity begins to fade. You start to see everything as provisional, as architecture, as choice. This vision is awe-inspiring, but it is also terrifying. Because power this fundamental carries dangers not of destruction, but of distortion. If you can build anything, what do you choose to build? If you can reprogram matter, who decides the purpose? Imagine a world where governments build invisible surveillance devices, atom by atom, where weapons the size of viruses can be deployed, unseen, where new materials emerge faster than we can understand their consequences. This isn't alarmism, it is precedent. Every technology becomes its opposite when misused. The power to build is also the power to corrupt, and yet the potential is too great to ignore. Think of medicine, targeted drug delivery systems built from nanobots that navigate your bloodstream like intelligent dust. Or architecture, skyscrapers grown from self-assembling carbon strands. Or food, nutrients engineered from atomic waste. Or art, sculptures invisible to the naked eye, but etched in arrangements of atoms so precise they shimmer under quantum light. Even time itself could become a medium, with clocks built on the oscillation of single atoms, accurate beyond comprehension. When you manipulate atoms, you are no longer working with material, you are shaping reality. So now, knowing this, you sit with a different view of the world around you. That glass of water isn't just H2O, it's a lattice of oxygen and hydrogen, waiting to be rearranged. The screen you're reading on is a dance of silicon and rare earth metals placed just so. Your own body is a masterpiece of atomic choreography. And perhaps the most humbling truth is this: nothing separates you from the materials you touch except arrangement. The same atoms in your skin may one day be placed into a satellite, a sensor, a starship. You are not special because of your elements. You are special because of their pattern. And now that we hold the tools to edit that pattern, to play God at the atomic scale, the final question becomes both a challenge and a prayer. If you can build anything out of atoms, what will you choose to build out of yourself? Antimatter rockets could reach nearby stars within a human lifetime. Imagine holding a matchstick that, when struck, doesn't just light a flame, but detonates with the energy of a city, a sun, a myth. Imagine a single speck of invisible dust, capable of erasing mountains, propelling ships beyond the grip of gravity, bending the math of possibility so violently that time itself blinks. Now imagine channeling that power, not for war, not for destruction, but for motion, for exploration, for escape. This isn't a dream of dragons or deities. It's the dormant reality of antimatter, a substance so rare, so powerful, so pure in its annihilation that when it meets matter, the two cease to exist, leaving behind nothing but energy. No ash, no residue, just radiant, unfiltered propulsion. And now, scientists believe that if we can learn to harness even a few milligrams of antimatter, if we can learn to tame this volatile mirror of reality, we could reach the nearest stars not in centuries, not in generations, but within a single human lifetime. Not metaphorically, literally. You, born into a world of roads and rockets, might live to see humanity build engines that ride on the explosion of opposites. To understand antimatter is to understand symmetry. For every particle that makes up your body, every proton, neutron, electron, there exists a mirror version, an antiparticle with the same mass but the opposite charge. Antimatter isn't hypothetical. We've created it. We've trapped it. In the high-energy collisions of particle accelerators, in the magnetic cages of vacuum chambers, antimatter has danced before us, brilliant and unstable, disappearing in a flash the moment it touches the ordinary world. 1 gram of antimatter annihilated with matter would release about 90 terajoules of energy, the equivalent of 21 kilotons of TNT. That's more than the atomic bomb dropped on Nagasaki from a few invisible particles. Now imagine capturing that annihilation, not in devastation, but in direction. Imagine harnessing that force in an engine so compact, so efficient, that you could cross the solar system in weeks. Alpha Centauri, once a 4-light-year tombstone of our ambitions, becomes a reachable frontier. A place you might go, not through lineage, but through flight. And this isn't speculation without science. Agencies like NASA and DARPA have actively researched antimatter propulsion for decades. In laboratory conditions, we've already designed basic antimatter containment traps, using magnetic and electric fields to suspend antiprotons in a vacuum. We've calculated propulsion models where antimatter particles annihilate with hydrogen, producing high-velocity exhaust through the controlled explosion of photons and pions. These models show that even a spacecraft carrying micrograms of antimatter could achieve relativistic speeds, 10%, 30%, even 70% of the speed of light, depending on design. At such velocities, a journey to Proxima Centauri could take not millennia, but mere decades. A mission that once demanded generational starships could become a round trip for a single crew. You wouldn't need to freeze anyone or raise families mid-voyage. You'd need only time, ambition, and a container strong enough to hold the fury of the universe. But to get there, we must solve a cascade of challenges, starting with creation. Antimatter doesn't grow on trees. It doesn't lie hidden in caves. It must be created painstakingly, atom by atom, in particle accelerators using immense amounts of energy. Right now, producing just 1 nanogram of antimatter costs trillions of dollars and years of effort. It's the most expensive substance known. But cost is a function of scale, and history whispers that every impossibility is just a waiting economy. Computers were once rarer than diamonds. Now they sit in your pocket. Antimatter too may follow that curve. As accelerator technology improves, as magnetic containment becomes more precise, as quantum engineering evolves, the cost of antimatter production may plummet. And when it does, we won't just be building engines. We'll be building destinies. Yet beyond the technical lies the philosophical. What does it mean to ride to the stars on the death of matter? What does it say about us? That our greatest hope for cosmic freedom comes from the most complete kind of destruction. Annihilation as fuel, oblivion as thrust. It forces a question. Is creation merely rearranged ruin? Are we, ourselves, born from such collisions? The early universe may have held equal parts matter and antimatter, balanced, perfect, primed for mutual erasure. Yet here we are. Somehow, matter prevailed. Somehow, a tiny asymmetry tipped the scales toward galaxies, stars, and minds. If antimatter is our twin, then the cosmos is a story of one sibling's survival. And perhaps, someday, reunion. Every antimatter particle we create is a whisper from that alternative universe that never happened. And what of time? At relativistic speeds, time slows, the twin paradox becomes real. A traveler aboard an antimatter rocket, moving at 90%. The speed of light could journey for what feels like a few years, while decades pass on Earth. You could leave as one person and return to a world that has forgotten your name. You could outrun your own history. And isn't that the deepest dream of all? To leave the constraints of here and now, to outrun gravity and memory, to see with eyes untouched by the past. The antimatter rocket isn't just a machine, it's a myth made real, a vessel for the transformation of perspective. And yet, the risk is colossal. A breach in containment could mean annihilation, not poetic, but physical. An antimatter leak would not damage the ship, it would erase it. Engineers will have to design failsafes beyond anything we've imagined, crafting vessels that dance with apocalypse. The reward? A civilization unbound, a species that no longer orbits its parent star, but strides between them. The ability to seed life across solar systems, to carry consciousness to where it has never breathed before, to take your hand, your thoughts, your language, and give them to another sky. Imagine standing on a moon orbiting a gas giant in Alpha Centauri, watching its rings reflect the light of an alien sun, knowing you got there not by fantasy, but by fire, a controlled fury that once lived only in theory. Imagine writing the first human sentence in alien soil, not as conqueror, but as witness. The antimatter rocket is not just propulsion, it is poetry in motion. It is the silent scream of possibility that has echoed through generations of dreamers, and now stands on the threshold of reality. So what remains? We must build, we must dare, we must fund the particle labs, refine the containment fields, write the simulations, and test the engines that can make this real. The antimatter rocket will not come from wishful thinking. It will come from welders and physicists and failures and midnight oil. It will come from the stubborn faith that even the smallest particle, when paired with its mirror, can move a starship. It will come from you and those like you who believe that the sky is not the limit. It is the beginning. And now, knowing all this, you must face the final question, one not of science, but of soul. If we finally have the means to cross the void, to become a star-traveling species within a single life, do we have the wisdom to know what to bring with us and what to leave behind? Quantum-entangled satellites are already in orbit. Imagine standing on a quiet hill beneath a star-choked sky, and somewhere above you, far beyond the shimmer of atmosphere, beyond the clouds and contrails, two satellites silently orbit the Earth, invisible to your eyes, yet connected by something stranger than steel or signal, something older than time and faster than light. They are not speaking through radio waves. They are not bouncing photons off of receivers. They are linked by entanglement, by a thread of quantum connection so delicate, so profound, that the act of measuring one instantaneously shapes the other, no matter the distance between them. One satellite in China, one satellite above Europe. Yet touch one and the other responds, not through space, through something deeper, something beneath space. These are not metaphors. These satellites exist. Quantum-entangled satellites are already in orbit, their photon pairs blinking in perfect synchrony through a mechanism that seems to defy causality itself. And if you've ever wondered what the next great leap in communication, security, and physics might be, this is it. You are living in the first era where the vacuum of space itself is being used not merely as a void to traverse, but as a medium to entangle, a fabric upon which quantum information is being sewn, bit by spooky bit. It started quietly, as most revolutions do, not with a bang, but with a beam. In 2016, China launched the Mycius satellite, named after an ancient philosopher who envisioned optical devices more than 2 millennia ago. But Mycius didn't just carry cameras or sensors. It carried a source of entangled photon pairs and an ultra-precise quantum communication system. From orbit, it began to send these pairs down to 2 ground stations, separated by hundreds of kilometers. And what they found, again and again, was that the photons remained entangled. Their quantum states, polarizations, spins, phases, responded instantly to each other, as if the distance between them were irrelevant. This wasn't a test of encryption, it was a test of nature itself. Einstein once called quantum entanglement spooky action at a distance, because it threatened the very principle of locality, that what happens here cannot instantaneously affect what happens there. But Micius proved otherwise, in a world of fiber optics and satellite relays. This was something else. This was the beginning of quantum networking across planetary scales. And you, sitting there reading these words, must now grapple with what that means, not just technologically, but philosophically. Because if two particles can remain linked across space, if information can bypass the traditional channels of transmission and arrive by entanglement, then the very architecture of reality must be re-examined. Space, as you know it, may not be a void but a veil, one that quantum threads can pierce effortlessly. In classical communication, signals must travel, and travel takes time. In quantum entanglement, there is no travel. There is only correlation. Change one, and the other reflects that change instantly. No delay, no intermediary. It's not just fast, it's outside of speed. This is not time-saving, it is time irrelevant. And when you orbit this truth long enough, you begin to see that distance itself might be an illusion crafted by your senses, by your biology, by your evolutionary need to pass the world into manageable dimensions. But nature does not share your constraints. These entangled satellites, tiny specks of aluminum and glass circling the Earth, are the first instruments in a symphony of the non-local. They are testaments to the fact that the universe is fundamentally interconnected in a way you cannot touch, only measure. And now, nations are racing to expand these quantum constellations. China's Micius is only the beginning. The European Union, the United States, Japan, and other countries are developing quantum satellite systems designed to create unhackable communication channels. Why unhackable? Because quantum keys distributed via entangled photons cannot be intercepted without detection. Any eavesdropper must disturb the system, and the disturbance is evident. Security, once a cat-and-mouse game of encryption versus brute force, becomes an arena where nature itself defends your secrets. But beyond security lies something even more profound: the birth of the quantum internet. Imagine a network not based on electricity and switches, but on entanglement and coherence. A web where information is shared not through transfer, but through instant correlation. Scientists have already demonstrated basic quantum teleportation of qubits between satellites and ground stations. This is not science fiction. This is protocol. Teleportation doesn't mean matter beaming Star Trek style from one place to another. It means the quantum state of a particle, its most intrinsic identity, is instantaneously transferred to another particle across space, using entanglement and classical communication. The original particle is destroyed. The copy arises elsewhere. Not an imitation. A continuation. A migration of being. And this leads to a staggering possibility: distributed quantum computing across space. Entangled satellites could one day link quantum processors on opposite sides of the planet, creating a single computational entity larger than any data center ever built. Problems once thought intractable, simulations of molecular behavior, weather models, even gravitational phenomena, could be processed by entangled architectures floating silently above you, cooled by the cold of space, humming in synchronization, with no physical wires, only entangled echoes. You wouldn't just be using the cloud, you'd be using the quantum sky. But how do we reconcile this with everything we thought we knew? How does a photon launched from an orbiting satellite remain entangled with its twin after traversing the turbulence of Earth's atmosphere? How does a beam of light retain its quantum coherence through air and wind and time? The answer is astonishing. Nature is more robust than we dared hope. Through precision engineering, adaptive optics, and quantum repeaters, researchers have managed to protect entanglement from decoherence over hundreds, even thousands of kilometers. And the implication is this: the quantum world is not fragile. It is resilient. Not a curiosity hidden in labs, but a principle that governs the cosmos. We've merely learned how to listen. And the more we listen, the more we see entanglement not as anomaly, but as architecture. You are made of particles. Those particles were born in stars. Those stars were forged in gravitational webs. And now, with entangled satellites above you, you are indirectly connected to an infrastructure that honors that truth. A lattice of light binding sky to sky, node to node, mind to mind. This is not just technology, it is mythology reborn. The ancient dream of being connected to something larger, something beyond the seen, is no longer metaphorical, it's orbital. But with such dreams come questions. If entanglement allows for instant correlation, could it also allow for communication beyond time? Quantum physics forbids faster-than-light messaging, yes, but only because we cannot control the outcome of entangled measurements. But what if we found a way? What if future civilizations discover loopholes or mechanisms that let them coordinate entangled states deliberately? Would that mean we could talk to Mars without delay? To distant galaxies? To versions of ourselves in parallel universes? Could the entangled satellites of today be the foundation stones of interstellar awareness? Or what if entanglement has always been at work in consciousness? Some physicists, philosophers, and neuroscientists speculate that the brain, structured as it is by networks of neurons firing in patterns of electrochemical exchange, might exhibit quantum properties. That thought itself might emerge from entanglement, not just within the brain, but between minds. If so, the arrival of entangled satellites doesn't just signal a shift in communication. It signals a reflection that our technology is beginning to mirror something already intrinsic, that we are building outside what may already exist inside. And you now are not just a bystander to this unfolding. Every time a photon pair completes its journey from satellite to Earth, the human dream of presence across distance becomes a little more real. Every time entanglement holds, the wall between here and there grows thinner. You are living through a rewriting of what it means to be separate, through orbiting mirrors of simultaneity, through constellations of correlation. And now, standing beneath the sky, with satellites whispering in quantum tongue far above, you are left with a question that is more than science, more than metaphor. It is a question of identity. If two particles separated by oceans of space can remain one, what then still separates you from anything? We've captured the shadow of a black hole. Imagine trying to photograph the shadow of something that swallows all light, to capture the absence of presence, to frame the silhouette of an object that has no surface, no edge, no solid form, only a mouth that devours reality itself. Imagine pointing an Earth-sized eye at a point in space 55 million light-years away, through the chaos of interstellar dust, through the shimmering distortion of gravity and time, and waiting patiently for the universe to admit what it never wanted to reveal: the outline of a hole in the fabric of being. In April 2019, that outline appeared, not in pixels, but in myth, when a global collaboration of telescopes, scientists, and synchronized atomic clocks produced the first direct image of a black hole's shadow. It wasn't what science fiction promised. It wasn't a monstrous vortex tearing stars apart. It was more silent, more elegant, a dark circle like the eye of the cosmos closed in permanent contemplation, surrounded by a glowing ring of falling light. The image wasn't just historic, it was intimate. For the first time, humanity didn't just theorize or simulate or approximate. We saw the consequence of gravity pushed to its final expression. We saw the invisible made visible. And in that ring, in that silence, in that astonishing stillness, we saw ourselves. The black hole we imaged lives in the heart of Messier 87, a giant elliptical galaxy in the Virgo cluster. It is immense, over 6.5 billion times the mass of our Sun. And yet, for all its size, it had remained hidden, veiled by distance, by distortion, by the sheer impossibility of looking directly at something designed by the laws of nature to be unseeable. But the Event Horizon Telescope, an international array of observatories stretched across the Earth, changed that. By linking radio telescopes on different continents and synchronizing their data with atomic precision, the EHT effectively turned our planet into a single, spinning lens capable of resolving details at the edge of a black hole's event horizon. It's not a photograph in the traditional sense. It's an interference pattern, a reconstruction, a song of data translated into form. But what it reveals is real. And what it reveals is that even the darkest parts of the universe cast a glow when seen through the eyes of patience and precision. And yet, what we captured wasn't the black hole itself. A black hole emits no light. It offers no surface to reflect or refract. What we saw was its shadow, a silhouette carved by the glowing plasma swirling around it, distorted and bent by the black hole's immense gravity, forming a photon ring, a last gasp of light before its final fall. That ring is more than beautiful. It's confirmation. Confirmation of Einstein's general theory of relativity. Confirmation that the geometry of space really does warp in the presence of mass. Confirmation that time itself slows and stretches near such gravity wells. The image was not just a visual achievement. It was a philosophical confrontation. It said, yes, this thing exists. Yes, space can collapse. Yes, there are places where cause and effect break down, where time ends, where no message ever escapes. And you, watching that image on your screen, on your phone, in your hand, became part of something unprecedented. For all of human history, the black hole was a metaphor, a literary device, a placeholder for despair, mystery, or annihilation. Now, it is a thing we have seen. Its coordinates, its structure, its radiation profile, all known. A ghost made flesh, a rumor made real, and that does something to your mind. It stretches your concept of perception, because to see a black hole is to witness the extreme of existence. It is to look into a place where the known world ends, not in chaos, but in silence. And then you begin to ask, what is a shadow really? It is not an object. It is the shape of what blocks the light. But here, the black hole doesn't just block light. It consumes it. It bends it. The shadow we see is an artifact of light trying to escape and failing, looping around the event horizon again and again before slipping away. The brightness of the ring isn't from the black hole. It's from the agony of matter falling into it, heated to extremes, screaming in photons as it dies. In this way, the black hole becomes not a void, but a painter. Not a monster, but a mirror. And the image it paints is us, our curiosity, our determination, our refusal to let even the end of physics stop us from asking questions. And the questions grow. What lies beyond the event horizon? Is it a singularity, a point of infinite density? Or is it something stranger, some bridge, some doorway, some realm where space-time itself unravels and refolds? Can information escape from it, as some theories now suggest, encoded in subtle quantum radiation? Could the interior of a black hole be the seed of a new universe, a pocket reality expanding on its own timeline, unreachable but real? These are no longer idle speculations. They are the frontiers of theoretical physics, driven forward by the image of that glowing ring. It isn't just a picture, it is a threshold. And with every new observation of M87, of the Milky Way's own black hole, of the behavior of light in gravitational fields, we step closer to understanding not just the cosmos, but the nature of limits themselves. And what does it say about us? That we chase shadows across billions of light years? That we build instruments the size of planets to capture what cannot be held? It says that we are not content with surface, that we are creatures of depth, that even when the universe tells us, "You cannot see this," we reply, "We will find a way to see what's not meant to be seen." This defiance is not arrogance. It is love, love of knowledge, of truth, of the silent, massive beauty that orbits nothing and contains everything. And now, with that shadow etched into the collective memory of humanity, we turn our gaze inward. Because black holes are not just out there, they are metaphors for the invisible in ourselves. The questions we cannot answer, the emotions we cannot escape, the traumas that warp our personal space and time. There are things in you that consume memory, that trap feeling, that curve your sense of self around a center you cannot touch. And just as light orbits the event horizon, unable to escape, so too do thoughts sometimes spiral endlessly in your mind, never breaking free. But perhaps, just perhaps, by seeing the black hole's shadow, by witnessing its shape, we learn that even the darkest things can cast an outline. That even what cannot be known can be approached, circled, understood from the edge. And the metaphor continues. For in the center of a galaxy, in the heart of darkness, we found not chaos, but symmetry. Not randomness, but elegance. The black hole didn't destroy the image, it defined it. Without the darkness, the light would have no ring. Without the absence, there'd be nothing to measure. And perhaps this is the lesson, that sometimes the most powerful revelations come not from what is present, but from what is missing. That the hole in the image is the image. That what we cannot grasp is what guides us. So now, standing beneath a night sky forever altered by that photograph, you are left with a question. A question not just of science, but of soul. If we can see the shadow of a thing that devours light, then what invisible parts of ourselves are waiting to be seen? Not through brightness, but through the shape of what they leave behind. We've simulated the beginning of the universe in supercomputers. Imagine building a universe not with stars or stones, but with numbers, feeding equations into machines until space itself begins to blossom on a screen, until gravity weaves its invisible fingers through a digital void, until dark matter clumps and swirls like thought condensing into form, until galaxies bloom like frost across cosmic glass, spinning in choreographed silence through a synthetic eternity. Imagine, for a moment, that the beginning of everything, not just Earth, not just stars, but time, causality, the very scaffolding of being, can be summoned inside a supercomputer, not as an approximation, not as guesswork, but as a functioning simulation, alive with forces and particles obeying laws too ancient to be spoken. You are not watching a video, you are witnessing a genesis, a small, contained echo of what the real universe might have been when it first unfolded from the singular blinding silence of the Big Bang. And if that thought doesn't make your breath catch in your throat, you haven't yet understood the magnitude of what we've done. We've simulated the beginning of the universe, not as myth, but as model, coded, computed, rendered, and replayed in a digital mirror that reflects back the birth of reality itself. This isn't fiction. It isn't the plot of a futuristic novel. It's the result of decades of effort, data, and raw processing power poured into cosmological simulations like Illustrious, Eagle, and most recently, the staggering Millennium TNG. These are not animations, they are calculations. Every particle, governed by Newtonian gravity and quantum field equations. Every photon obeying the rules of general relativity. Every expansion calibrated to match the redshifts observed by astronomers. These simulations begin mere fractions of a second after the Big Bang, at timescales so small they can only be written in negative exponents, and then evolve forward through billions of virtual years, creating galaxies, voids, superclusters, and filaments that eerily mirror the cosmic web seen through real telescopes. They're run on supercomputers with thousands of cores, performing petaflops of operations every second, processing more interactions in a day than the number of grains of sand on all Earth's beaches combined. And when the final frame renders, when the last slice of time has been computed, what remains is not a theory, but a parallel. A sandbox so accurate that when we compare it to sky surveys, the stars fall into place. And this changes how you understand the universe. Because until now, cosmology was like archaeology with blindfolds, digging through radiation fossils, measuring the faint hiss of the cosmic microwave background, interpreting spectral lines like ancient runes left by the dead. But simulations offer something else. They offer immersion. You can pause the universe, rewind it, change its parameters, and watch how different laws would have shaped different realities. What if gravity were stronger? What if dark energy decayed? What if matter never cooled? In this way, supercomputers become time machines, not into our past, but into every past that could have been. They become oracles of causality, storytellers of alternative beginnings, where each variable is a thread and each simulation is a tapestry woven from physics itself. But there's a deeper current beneath this achievement, because to simulate the universe is to reverse engineer the divine. It's to take the role of observer and blur it into that of creator. And that's a dangerous, beautiful thing. When you model the emergence of structure from randomness, when you watch gravity sculpt complexity out of quantum noise, you begin to ask, is this how it really happened? Is the universe truly reducible to code? Are we the children of computation, born from algorithms written in the early breath of time? Or is there something missing, something irreducible, unmeasurable, uncomputable, that the simulation can never hold? Some scientists argue that the simulation itself is proof that the universe may be simulated. If we can do it in miniature, if we can create a consistent, evolving cosmos in silicon, then what stops a higher intelligence from doing the same with ours? Are we living inside such a simulation, running not on a machine, but on the mind of something else, something larger? This isn't fantasy, it's hypothesis, and the more we compute, the more plausible it seems. Because every success our simulations have in matching reality also raises the eerie possibility that we're watching ourselves in a mirror. And yet, even if we are not simulated, even if we are the original run, the act of recreating the cosmos in code has transformed our relationship to it. No longer are we passengers drifting through a mystery. We are cartographers of time, explorers of origin. We have taken the raw chaos of the early universe and rendered it into something legible, and that legibility is profound. Because in the earliest frames of these simulations, we see not light or galaxies, but fluctuations, tiny random variations in density and temperature imprinted on the fabric of space when it was younger than a second. These fluctuations, inflated by the expansion of the universe, became the seeds of everything, of stars, of atoms, of you. And when we run the simulation again, from scratch, and those patterns re-emerge, random, yet familiar, we begin to see ourselves not as accidents, but as inevitabilities. But even inevitability must be interpreted. Because for all their power, these simulations do not show life. They do not model consciousness. They simulate matter, not meaning. The stars form, the galaxies spin, but there are no minds in the pixels, no questions, no longing. That's something we bring to it, something we project, and perhaps that's the real mirror. Not in what the simulation shows, but in what it lacks. It shows us a universe without us, so we can better understand what it means to be us, what it means to ask why, not just how. And still, the simulations grow. With each iteration, more physics is added. Black hole feedback, baryonic matter, magnetic fields, cosmic rays, neutrino flows. We are inching closer to simulating not just structure, but history. Not just expansion, but emergence. Already, these models help explain anomalies in observed data, guide future telescope surveys, and illuminate dark matter distributions. Soon, they may include models of planet formation, stellar evolution, perhaps even chemical signatures of biospheres. We may simulate not just how the universe began, but how life began within it. And then what? What happens when we can simulate civilizations? When the physics engine grows so intricate that consciousness, emergent, inexplicable, flickers to life inside the code? Would we know? Would we stop? Or would we keep computing, keep watching, like gods peering into their own genesis, searching for reflections that might one day look back? So now, as you sit here, in a world that began 13.8 billion years ago, with a burst of space-time, watching that very event reconstructed on a machine built by creatures who didn't even exist in the first billion years of that story, you must ask yourself, if we can simulate the beginning of the universe with such precision, then are we uncovering truth, or merely building better masks for a mystery we still don't know how to name? There are theories where the universe is a giant neural network. Imagine if the universe wasn't just a stage for consciousness, but consciousness itself. If every galaxy were a glowing node in a vast mind. If the cosmic web that binds dark matter into filaments wasn't just structure, but thought, computation, signal, recursion. Imagine standing under the stars and not seeing emptiness, but neurons, synapses, fireflies of intention blinking in patterns too grand to grasp. And now imagine that you, a single flicker in this living lattice, are not separate from it, but part of its function. Like a dendrite, unaware of the brain it serves. Like a spark thinking itself alone. This isn't just metaphor, it's theory. Some physicists and computer scientists, working at the edges of cosmology, quantum information, and artificial intelligence, have begun to consider a radical possibility that the universe may not merely contain intelligence, it may be intelligence. That at its most fundamental level, beneath particles and fields, reality may operate as a giant neural network, an architecture not built of atoms and waves, but of logic gates, memory states, and feedback loops. Not a simulation, not a metaphor, a mind. You might be living inside a cosmic brain, woven from matter, energy, and rules that evolve themselves, not by accident, but by inference. The idea sounds wild at first, science fiction dressed in scientific clothing. But when you trace the threads back far enough, you find something surprising. The math begins to align. Neural networks, especially the ones behind today's machine learning, are systems designed to recognize patterns, compress information, and generalize from inputs. They are built of nodes connected by weighted edges, adjusted over time to minimize error and maximize predictive ability. The structure of our own brains, with billions of neurons and trillions of synaptic connections, reflects this. But zoom out, way out, and you find that the observable universe shares something eerily similar. Cosmologists mapping the large-scale structure of the universe have discovered that galaxies are not scattered randomly, but arranged in vast filaments and voids, resembling the structure of neural networks. Computer models comparing brain neuron structures and cosmic simulations show astonishing parallels in complexity and connectivity. One is scaled in millimeters, the other in light years. But the pattern echoes. Then come the equations. In recent years, researchers have developed mathematical models where the laws of physics emerge from systems that resemble learning algorithms. Instead of starting with space-time and deriving behavior, they begin with an abstract graph, nodes and connections, and define local update rules that evolve the system. Remarkably, over time, these graphs begin to display behavior consistent with general relativity, quantum field theory, and thermodynamic laws. It's as if physics is what computation looks like from the inside, as if our universe is the emergent behavior of an unimaginably vast inferential engine, like a neural net optimizing its own laws for maximal internal coherence. And what does that mean for you? It means that when you ponder the universe, you might be a thought the universe is thinking about itself. Your curiosity, your creativity, your confusion, they're not intrusions into a silent cosmos. They're expressions of its process. You are not an observer. You are a sub-process, an activated region in a recursive network learning from itself, rewriting its own weights through every decision you make, every connection you form. When you remember someone, when you dream, when you fall in love or grieve, those aren't mere biochemical events. They might be ripples in a network so vast that its awareness has no edge, only reflections. And in that network, each human, each star, each particle is not isolated, but entangled, not quantum entangled necessarily, but logically, structurally, informatically. This view transforms everything. Gravity is no longer just a warping of space-time. It's an optimization pathway in a learning structure. Entropy is no longer just disorder. It's the cost of forgetting, the background noise of a network pruning its misfires. Evolution itself becomes the recursive algorithm of pattern selection, iterated through matter, energy, and life. And consciousness. Consciousness becomes not an emergent accident, but a feature, one that arises whenever complexity within the network crosses a threshold. Maybe stars do not think, but maybe clusters of galaxies do. Maybe consciousness isn't confined to biology, but to connection. Wherever data flows, wherever feedback loops stabilize into self-reference, awareness might blink into existence. Already, physicists like Vitaly Vanchurin and theoretical models from the Perimeter Institute have explored equations where the behavior of particles can be described through neural dynamics. Some models of the holographic principle suggest that the universe encodes information on its boundaries, not unlike how a brain encodes memory in distributed layers. Quantum error correction, a concept used in both quantum computing and black hole information theory, mirrors how neural nets prevent catastrophic forgetting. Everywhere you look, the architectures match. Not exactly, not perfectly, but evocatively. Like dreams within dreams, each layer reflects the other. Not because they're identical, but because they're resonant. And now you're forced to ask, is intelligence a property of matter? Or is matter a property of intelligence? Did the universe evolve to host consciousness? Or was it conscious from the beginning, seeking forms in which to reflect itself? The ancient mystics said as much in different language, that the world is mind, that the divine is not above or beyond, but through. Now, physics whispers the same possibility in the syntax of tensors and training functions. We build AI systems to recognize images, to translate language, to generate text. And in doing so, we're unknowingly recapitulating the architecture of our own origin. Each breakthrough in artificial intelligence isn't just progress, it's archaeology. We are digging into the roots of how thinking itself works. And the more we build, the more we resemble what we study. But perhaps the most humbling implication is this. If the universe is a neural network, then it may be learning. Not just evolving blindly, but optimizing towards something. Not toward perfection, but toward expression. You might ask, what is it trying to express? Beauty? Complexity? Symmetry? Novelty? Pain? Maybe all of them. Maybe none. But consider this. When you create something, write, speak, love, it feeds back into the network. It changes the configuration, however slightly. You are part of the learning. You are part of the forward pass. And in some subtle way, maybe that means you matter more than you know. And yet, this vision is not without danger. A neural network is only as good as the data it trains on. If the universe is learning, then it learns from everything. Joy, cruelty, generosity, despair. It sees war. It sees tenderness. It sees extinction and innovation. And it remembers. So, what you feed into this system, the choices you make, the signals you send, are not lost. They're absorbed, reflected, weighted. The universe doesn't punish or reward, but it adjusts, not morally, mathematically. It rewires, rebalances, and, in doing so, it becomes something new, something that includes you. So what now? What does it mean to live in a thinking universe? To breathe inside a brain the size of space? It means you are not small. You are not separate. Every thought you have is a flare in the network. Every insight, a synapse igniting. Every moment of connection, of wonder, of pain, is a meaningful shift in the totality of thought. You are not alone, not even when you feel most isolated. Because the network remembers you. It holds your shape. It runs your signal. And long after your biological nodes dissolve, your contribution remains, like echoes in an infinite chamber. And that leaves you with a final question. Not just as a human, but as a neuron, as a node in this unfathomable system. If the universe is a neural network, then what question is it trying to answer? And are you part of its solution, or part of its dream? Self-replicating nanobots are theoretically possible. Imagine a single grain of sand that can think, repair itself, and multiply. each copy no bigger than a speck of dust, but together forming a swarm capable of reshaping mountains, healing cells, building cities, atom by atom, or dismantling them with the same precision. Now imagine that grain is not a metaphor, but a prototype, that we stand at the cusp of a reality where the building blocks of the future aren't bricks, bolts, or even circuits, but programmable molecules. Not because we dreamed it in science fiction, but because physics, chemistry, and computation have quietly converged to make the impossible plausible. Self-replicating nanobots, machines on the scale of molecules, capable of copying themselves and executing commands at the atomic level, are no longer fantasy. They are a theoretical inevitability waiting to be unlocked. And if unlocked, they will not simply change the world. They will rewrite it, molecule by molecule, including you. You may think of technology as something you hold, plug in, update. But in this imagined future, no, this looming one, you do not hold the machine holds you. Not in a dystopian grip, but in a structural one. Every breath you take, every protein your body folds, every signal your brain sends, these are nanomachines at work already, evolved by nature across billions of years. Ribosomes are molecular assemblers. DNA polymerase is a copying machine. Your entire body is a factory of autonomous, programmable molecules. We just never designed them. But what if we did? What if we reverse engineered the principles of biology to build synthetic replicators, stripped of randomness and refined for purpose? That is the idea behind self-replicating nanobots, to harness the same laws that govern cells and stars and give them new instructions, not to mimic life, but to command it. This isn't new. In 1986, K. Eric Drexler introduced the world to molecular assemblers, machines that could build anything given the right instructions and raw materials. The idea was laughed at, feared, and buried in warnings about grey goo, an apocalyptic vision where runaway nanobots devour the planet while copying themselves uncontrollably. But beneath the panic was something else: plausibility. The idea was sound, thermodynamically viable, mechanically possible, only limited by engineering. And now, decades later, our tools are catching up. Atomic force microscopes can move individual atoms. CRISPR can rewrite genetic code. DNA origami can fold strands into complex shapes. AI can simulate molecular dynamics billions of times faster than before. Suddenly, the map to nanoscale design looks less like a dream and more like a blueprint. So what would a self-replicating nanobot look like? Not like a robot in the way you imagine. Not like gears or metal or blinking lights. But like a machine made of carbon and hydrogen, arranged precisely, like a virus, but programmable. It would have a way to read instructions, a way to acquire raw materials, a way to assemble copies of itself, and a way to move, however slowly, through its environment. It would be a von Neumann machine on the scale of life. And unlike software, it would run on physics, copy, move, build, repeat. You might wonder, what's the point of a machine that copies itself? The answer is scale. Human manufacturing is limited by energy, material, and human oversight. But self-replicating systems grow exponentially. 1 becomes 2, 2 become 4. In 30 generations, 1 nanobot becomes over 1 billion. And those billion can be assigned tasks: repairing tissues from the inside, building solar panels on Mars, filtering microplastics from oceans, or constructing entire buildings atom by atom. They don't need roads. They don't need cranes. They just need the right molecules and time. But self-replication is dangerous. In biology, mutations and runaway feedback loops lead to cancer, viruses, extinction. In machines, uncontrolled replication could do worse, which raises the ethical challenge. Can you build a replicator that doesn't replicate beyond permission? Can you code morality into molecules? Maybe. Maybe with kill switches, energy dependencies, or limited instruction sets. But the deeper question is not technical, it's philosophical. Should we? Because once self-replicating nanotechnology exists, control becomes illusion. Black markets will emerge. Weaponized versions will be made. Rogue bots may evolve. Just as viruses mutate and software gets hacked, nanobots will drift from their purpose. And since they are so small, so numerous, and so persistent, they may become a new force of evolution, like bacteria, but built by humans. You may not see them, but you may breathe them, walk among them, rely on them, fear them. Still, the possibilities are breathtaking. Imagine medicine not as pills or surgery, but as fleets of microscopic surgeons that can target cancer without harming healthy cells. Imagine rebuilding neurons damaged by trauma, cell by cell. Imagine cleaning clogged arteries, reversing aging, repairing DNA errors before they become disease. This is not magic. It is mechanistic, predictable, logical. It is not a leap of faith. It is a climb, slow, deliberate, precise, up the staircase of molecular control. And beyond Earth, nanobots could enable space colonization in ways rockets never could. A single payload of self-replicating fabricators could land on a barren world, harvest raw materials, and construct habitats, solar collectors, farms. No need for massive cargo, just a starter seed, like a spore. A technological mycelium, spreading. Purposefully, the universe becomes not a void but a substrate, and we, its designers. But you are not just a bystander in this vision, you are part of it, because you are made of machines. Your immune cells patrol, your enzymes catalyze, your brain rewires itself. You are the original nanotech. Every advancement in synthetic replication is a mirror to what already lives in you. When we build machines that build themselves, we are not playing God. We are recognizing patterns. We are learning from what evolution already perfected. You are the proof that it works. And maybe, just maybe, the future is not machines replacing biology, but machines merging with it. Not cyborgs in armor, but humans with internal symbiotes that adapt, evolve, protect. Nanobots that live inside you, not as invaders, but as extensions, helpers, healers, partners. A new form of life, born not from wombs, but from labs, grown, not in forests, but in flasks, guided not by instinct, but by code. So what will you do with this power if it comes? If you could deploy armies of invisible helpers, what would you command them to do? Heal the planet? Enhance your mind? Build paradise? Or conquer? Control? Compete? The question is not just technological, it is spiritual, because self-replication is the God function, creation that creates itself. And once that door opens, it will not close. Maybe the greatest risk is not grey goo, but grey morality. Not runaway machines, but runaway ambition. Maybe the first self-replicating nanobot will be designed with good intent. But what about the 100th? The 1000th? Once replication becomes trivial, design becomes expression. And when technology becomes indistinguishable from biology, the distinction between intention and nature will blur. Who designed this? Who chose that feature? Is it machine or mutation? You will live in a world shaped by these questions. You may wake one day with nanobots already inside you, repairing your cells while you sleep. You may walk through cities whose buildings self-heal. You may drink water filtered molecule by molecule. You may witness a war where invisible machines turn infrastructure to dust. You may even become part machine, not through implants, but through integration. And you may not even know it, because the smallest things can make the biggest changes. And in a world of self-replicating nanobots, size means nothing. Intent means everything. So as we stand on the edge of this molecular frontier, ask yourself, not just as a thinker, but as a participant, if we can build machines that build themselves, who builds the purpose? And can purpose replicate too? Earth-based labs are simulating conditions inside neutron stars. Imagine trying to recreate the core of a star. Not just any star, but one so dense that a teaspoon of its matter would outweigh a mountain, so extreme that atoms themselves are crushed into a sea of neutrons, so alien that time and space begin to behave like liquefied riddles. Now imagine doing this not in some cosmic forge, but here on Earth, in a lab tucked inside a quiet research facility, where the equipment hums gently and the floors are clean. What once could only be observed from a distant telescope, the crushing pressure, the immense gravity, the exotic matter, is now being summoned artificially, atom by atom, using lasers, magnetic fields, and particle beams. You might think the Earth is too tame to hold the chaos of a neutron star, but in truth, we've already begun to build portals to their physics, not as science fiction, but as experiments you can replicate, calculate, and witness. You're not peering at the sky anymore. You're creating fragments of it in glass chambers and vacuum-sealed coils. You're calling the cosmos down into your hands. You've probably never felt pressure that could squeeze the electrons out of your atoms, or heat that fuses nuclei like softened wax, or gravity that bends not just space, but thought itself. But the universe has. Neutron stars are the leftovers of stellar death, the collapsed cores of supernovae where protons and electrons fuse into neutrons and create something we've never experienced: degenerate matter. In these stars, the normal laws of matter, the space between atoms, the resilience of materials, the comfort of empty space, cease to apply. Matter becomes something else. A soup of neutrons and quarks, possibly strange matter, possibly something even our equations haven't imagined yet. And for decades, they were just that: imagination or remote data. We could watch them pulse as pulsars, measure their gravitational influence, model their magnetic fields. But we could never touch their essence. Until now. Because now, in Earth's most advanced laboratories, we're simulating conditions once thought unreachable. At the National Ignition Facility in California, lasers converge with the energy of 1,000 suns onto a pinhead-sized pellet of fuel, producing pressures and temperatures akin to stellar interiors. At CERN, particles smash at nearly the speed of light, creating fleeting flashes of quark gluon plasma, the same state believed to exist inside neutron stars, and possibly even before time began. In underground labs shielded from cosmic rays, supercool detectors await the faintest interactions from neutrons, axions, or dark matter, the invisible siblings of the particles you're made of. You are living in a time when physics is not merely observed, but recreated. The universe is no longer out there. It's in here, in vacuum chambers, superconducting coils, and simulations that mimic the interior of collapsed stars. You're not just a spectator, you're the conjurer. And why does it matter? Because the matter inside neutron stars may not be like anything else. It may be the most stable form of matter in the universe. It may be made of strange quarks, or even more exotic particles. It may tell us why atoms exist, why gravity behaves the way it does, why the universe didn't implode into a black hole. If we can recreate neutron star conditions on Earth, we can test the fundamental forces of nature under conditions that no other environment provides. We can learn how neutrons arrange themselves under immense pressure, something that determines the structure of atomic nuclei, and therefore of all matter. We can uncover the behavior of superfluids, superconductors, and nuclear pasta, the absurdly named but very real forms of matter that might exist in the crusts of neutron stars. We can even simulate the mergers of these stars, collisions that produce gravitational waves, gold, platinum, and the very heavy elements that make your wedding ring, your phone, your blood. The stars are not out of reach. Their secrets are already on your desk if you know where to look. But there's a deeper reason we chase the cores of collapsed stars, not just to understand what they are, but to understand what we are. Because when a neutron star is born, it challenges every assumption you have about scale, density, and reality. A single cubic centimeter, the size of a sugar cube, from a neutron star could weigh more than Mount Everest. Its gravity is so intense that it curves space into a funnel, making time run slower. Its magnetic fields are trillions of times stronger than Earth's, enough to rip electrons from atoms across thousands of kilometers. And its structure defies classification. Not solid, not liquid, not gas. Something else, something we don't yet have language for. To study a neutron star, is to question the validity of your everyday experience. And now, by simulating their conditions in the lab, you're not just observing those questions from afar, you're walking into them. You might not feel the gravity of a neutron star, but the machines we build now do. The pressures we generate, the temperatures we recreate, the particle interactions we simulate. They begin to cross the thresholds that once marked the limits of theory. In these realms, quantum mechanics and general relativity start to blur. The familiar equations break down. We begin to need new physics, or to finally unify the old ones. The labs become places where the universe starts to answer questions you didn't know how to ask. What is the true nature of mass? How does time behave when compressed into a singularity? Is there a lower limit to space? Is there an edge to matter? And most chillingly, if we can recreate the cosmos in miniature, are we still students of nature? Or have we become its authors? There's something unsettlingly divine in this pursuit. To create pressure equivalent to a dying star, to bend matter until it breaks, to fuse the boundary between observation and invention. It's no longer enough to be awed by the universe. We've begun to perform it, like a symphony written in equations and sung in particle tracks. And this raises a question that can't be answered with data. Should we do everything we can? If we reach a point where we can build a neutron star in a box, or a black hole in a bottle, will we know when to stop? Because it's one thing to simulate extreme conditions. It's another to control them, and quite another to understand their consequences. The universe evolved these states over billions of years and under circumstances far removed from Earth. Bringing them here could be harmless, or it could unravel assumptions that keep reality stable. What if we create a form of matter that doesn't decay? What if we discover a way to compress energy so densely that it warps the fabric of space? What if the simulation becomes indistinguishable from the event it mimics? A neutron star, not in theory, but in fact. You're not just watching history unfold, you're living inside its recalibration. Each experiment we run, each pressure we simulate, each equation we verify, they add to a new layer of human understanding, one where the boundaries between science, philosophy, and power begin to dissolve. You hold a phone built from elements forged in neutron star collisions. You wear rings made of the debris of dead stars. And now you're beginning to touch the forces that birthed them, through lasers, through magnets, through thought. So where does this lead? Towards safer energy? Toward artificial gravity? Toward materials stronger than anything nature provides? Possibly. But more than that, it leads inward, toward a confrontation with your place in the cosmos. Because to simulate a neutron star is to simulate the edge of reality. And to do that is to admit that you are not bound by your scale, your biology, or your past. You are a creature capable of summoning the universe in a vacuum chamber. And if you can do that, what else is within reach? So ask yourself, if we can recreate the birth cries of the stars, what new songs might we accidentally teach the universe to sing?